permit people to join us. So welcome to this special edition of the GGI Tea Breaks, dedicated to Steven Weinberg and the impact of his research and his legacy in theoretical physics. Steven Weinberg was a giant, a founding father of the theory of fundamental interactions and one of the greatest scientists of the last century. As is well known, his work has been a source of inspiration for generations of physicists, and it is at the heart of current frontline research. His conceptual breakthroughs in particle physics, quantum field theory, and cosmology still form the foundation of our understanding of physical reality. I must confess that I did not know how wide was the area of the research covered by Steven Weinberg and the number of topics where he contributed in a seminal way. Of course, everyone knows that he won the Nobel Prize in 1979, which is shared with Lesho and Abdul Salam, for his work unifying two of the nature's fundamental forces. In fact, he realized that by applying the Peter Higgs mechanism to the weak force, he could describe in a unified way the electromagnetic and weak interactions. And this became a foundation for the current standard model of particle forces. But Weinberg's research touched on many other areas. It's amazing the list of important results that carry the Weinberg name. Just to remind some of them, the Weinberg sum rules, the Weinberg operator, the Weinberg angle, the Weinberg-Witten theorem, the Lee-Weinberg bound, the Weinberg soft graviton theorem. And in addition, there are his groundbreaking contributions which do not carry his name, including the development of the effective field theories and cosmology. This event was to be a celebration. Do you hear me? Maybe they are calling for some problem. I hope you hear me. This event wants to be a celebration of Steven Weinberg. His contribution will be put into historical context and its relevance for present-day research will be discussed. The program includes 4 talks, each focused on a particular broad area of research where the work of Weinberg led the breakthrough progress. The speakers of the day do not need any introductions since they are very well-known eminent scientists, and I'd really like to thank them for accepting to give a talk for this Weinberg celebration. And also I'd like to thank the GGI Tea Breaks organizers, with whom I'm sharing every effort to make this day a great day, especially for the youngest generation of physicists. People are still connecting on Zoom. We are quite a number. And as I told you, for those who were not able to attend, the event is live streamed and you can find in the chat the link for the live streaming. All the infos are in the chat, yes, and the videos of the talk will be uploaded on the GGI webpage in the next days. Some details about the organization. We will have 2 sessions of 2 talks each, divided by 20 minutes of break. At the end of each talk, there will be a Q&A session and an overall free discussion at the very end of the day. Roberto Contino and Enrico Trincherini will coordinate the Q&A sessions, and I want to thank them for doing this job. So please write your question in the chat. That's all from my side, and I invite Roberto to open the session and to make to clarify other points that maybe I forget to do. Thank you again, and Roberto, please.
So thank you, Stefania. I think you clarified most of the things. As you say, I mean, the presentation of the speakers will be very, very, very short. Concerning how the event will evolve, I think we can devote the 10 minutes after each talk to the more specific questions on each talk, and then reserve the more general questions and comments to the final discussion session. So the first speaker is Ricardo Barbieri. So Ricardo is professor at Scuola Normale Superiore in Pisa. He is certainly an expert of the standard model, which is the topic of his talk. The title is The Standard Model of Particle Physics. He made very important contributions, in particular regarding precision tests of the standard model, where he's an expert. He is also very well known for his work on naturalness of the standard model as an effective field theory. And also he worked and made important contributions on flavor and CP violation. So please, Ricardo, you can start.
Thank you very much. I suppose I have to share the screen, right?
Yes.
Is that fine?
Yes, perfect. Thanks.
Very good, very good. So, well, for what has already been said about Weinberg, I am very, very glad to be able to give this talk, in particular on the standard model, because I believe that the standard model in its present form or in some modification of it that may arrive is one of the main achievements ever in the physical description of reality, or at least in an important quadrant of it, constituents and forces. Now, given that fact, it is not a surprise that it has taken a long time to construct it. Nevertheless, since in fact I claim that it's more than 100 years that has taken, I feel important to go through the story, which I plan to do in the way that you see. I will spend some time in describing the making of the standard model, which dates I will defend. I will briefly go through the successes of the standard model, and I will also try to reserve some time for the future of the standard model, because I think that in fact the story is not yet over. Okay, so the making of the standard model. Let me try to reduce my, yes, okay. Now, before entering into the subject, the broad view and the Weinberg legacy, you see the making of the standard model is made, of course, of the content, meaning the construction on effective field theory of the weak and the strong interaction. The strong interaction in parentheses, because in fact this will be more touched by other speakers, in particular over Giorgiai next to me. And then a full-fledged theory of the weak and the strong interaction. But, you know, equally important is to consider the methodology that was used, also made of two different directions: a phenomenological approach, new concepts to agree with experiments, and the search for mathematical logical consistency. Now, everybody of us knows that Weinberg has been a leading actor in B, in constructing a full-fledged theory of the weak and the strong interaction. But in fact, as it will become clear in my talk, I think he was a leading figure in A as well. And the thing that I want to underline most, a master of equilibrium between 1 and 2. Weinberg, as it has already been said, but even with respect to the approach, has not been a specialist in the best sense of this statement, and I think that this is part of his legacy. All right, so yes, all right. So I begin with really the beginning. the first thing that entered into the game was the realization in experiments mainly in the UK that the beta decay, the beta particles in beta decay had a continuum spectrum. That became clear between 1910 and 1920, generating a big discussion, even putting forward the possibility that there was a crisis of the energy conservation law. As we know, the issue was essentially resolved by the hypothesis put forward by Pauli of his neutron, quote unquote, which was a new particle of speed 1/2. And then what in all respects can be considered as the beginning of an effective theory of the weak interactions is Fermi Theory, where, allow me a bit of chauvinism, I quote the title in Italian, Tentativo di una teoria della emissione di raggi beta, which I suppose I don't have to translate for you. And that is the form of the interaction Hamiltonian that Fermi wrote in his very first paper. You recognize everything except perhaps the tau plus, tau minus, which were the raising and lowering operator of isospin as people were using in describing the nuclear interactions. Pretty soon, the more standard notation was introduced that you recognize with the various Lorentz invariant pieces, and again soon recognized to be problematic this interaction Lagrangian in its high energy behavior, because people noticed that, for example, the cross-section for the elastic interaction, the quasi-elastic interaction, was growing like the square of the momentum of the neutrino or of the energy. And in fact, in the 60s, gradually reduced to the current form that we are all familiar with and that you see written down there. Of course, I don't have to recall you that in the 50s, parity violation was discovered as strangeness was discovered, the various strange particles. The leptonic current was clearly written down in the form that we know now, in fact, including also the muon, which I didn't write down. The question was, what about the hadronic piece? Because nobody had a model for the strong interaction. And the key step that was recognized as essential to go forward was to associate the current describing the strong interaction with the symmetry of the strong interaction, because that would have allowed to make consideration to some extent model independent. So in 58, one put forward the consort vector current, essentially the identification of the vector piece of H mu with the isospin charge current, which made possible to establish beta decay and mu decay universality, because that observation allowed a normalization of the current and of the matrix element, and people were able to realize the universality with beta decay and mu decay. The axial part of the current was more of a problem, but in 1960-62, people introduced the concept of partially conserved axial current, chiral invariance spontaneously broken, pions perhaps as non-Goldstone bosons. And in 62, in fact, one of the first important contribution of Weinberg to this specific area was a paper written with Goldstone and Salam, showing that in general, pretty general terms, that the continuous symmetry and the non-invariant vacuum give massless scalars. At the end of the paper, in fact, the question was raised as to whether this had to be considered as a difficulty, because after all, nobody had seen massless scalars, and we will see how this will go forward. 63, a fundamental step by Cabibbo, who essentially enlarged the SU2 to SU3, the current written alla Cabibbo with the Cabibbo angle you see it written here, right, with the delta S equals 0 and the delta S equal 1. But the most important contribution of Cabibbo was that he understood that by thinking of this current as a piece of SU3, it was possible to make a quantitative comparison of all the strange particle decays, and indeed show that a current like this with the Cabibbo angle was capable to successfully predict all these decays. 64, Gell-Mann enlarged the SU2 cross SU2, if you want, including the observation of Cabibbo, to U3 cross U3, the algebra of current, as it was called at the time, which one can see it as a product of two U1s and two SU3s broken down to U1 vector cross SU2, SU3 vector. The axial part of this U1 will have to be the issue of the axial part, the fate of the axial part will have to be understood later on. Immediately after, Weinberg started giving a series of contributions, more than one paper, where in his usual style, he translated the algebra of current in a dynamical way of describing their contribution by means of effective chiral Lagrangians, applied to pions, baryons, the rho even. As he was saying, current algebra without current algebra. And I suppose that this will be again covered by G.G.I, but this is one of the characteristic way in which Weinberg likes to work, right? Writing down most general Lagrangians consistent with the symmetry and see the general consequences of those Lagrangians. Now, from the phenomenological sort of approach, one passes to the steps towards a full-fledged gauge theory. Now, of course, that proceeded very much in parallel to, excuse me, yes, to the phenomenological approach. Of course, everybody knows the story of U1 electromagnetism, of QED, and also of speculation that took place in that period about SU2 of isospin as a possible gauge theory, often derived from a five-dimensional theory, interestingly enough. A major step was made in 1954, everybody knows. Young-Mills gauge theory was written down for SU2, and in connection with the phenomenology of the weak interaction, an important step by Schwinger that started rewriting, if you want, the interaction Hamiltonian in a way that is more to which we are more accustomed to, and even trying to discuss the inclusion of a full triplet of vectors that he called Z plus minus, and the neutral and the zero component in a triplet of SU2, trying to identify the zero component with the photon. Yes, now the other steps, very important and also very well known that nevertheless it's worth recalling, is Glashow, that was the first to write down as far as I can tell, the algebra of the generators of SU2 cross U1 as the important generators of gauge symmetry of the electroweak interaction, and even introducing the notion of superposition of the two neutral components here in such a way as to construct the photon. Of course, a major question at that point was where the vector masses were coming from, not to mention the issue of including strangeness and so on and so forth. But this was certainly a major step. In the same year, I think Glashow and Gell-Mann, I think, extended the SU2 of Young-Mills to an arbitrary algebra, started talking of and thinking of a possible unification of all the interaction into a single compact group. The other major steps that we all know about is the Braut and Glert X mechanism with no massless particle anymore, but a massive scalar. And this, of course, is the major step forward that I think Weinberg was perhaps the first to realize how important it was, given the fact that he had suffered the problem of massless particles according to the Goldstone-Salam-Weinberg paper. Okay, so we are at 1967, and the title of the paper that I suppose many of you know and have written, and have read, whose title was A Model of Leptons. Now, I liked to copy this equation from the paper. You see, 4 is the number, the quote of the number of equations in the paper, because you will agree with me if I say that it's not frequent that nowadays you can take an equation from a paper which is 50 or 60 years old and use it, for example, when you give a lecture on the subject. This is the explicit complete Lagrangian for the electroweak interaction, at least for the leptons. Now, which were the important steps that Weinberg realized in that paper? I think the use of spontaneous symmetry breaking, SU2 cross U1 into U1, at least in 3 different directions. First of all, used for the first time in weak interactions, right? As I said, the spontaneous breaking of a symmetry was already discussed in the context of a strong interaction, but this is the time in which this spontaneous symmetry breaking is used in the context of the weak interaction. Of course, in generating vector boson masses, and in the paper, you find the correct lower bounds that, given the knowledge at the time, you could draw on the mass of the W and the mass of the Z. You see, the mass of the W had to be greater than 40 GeV. Of course, these numbers exactly reflect the knowledge of GF at the time. The correct number are perhaps 5 or 10% lower, but essentially correct. The lower mass of the W is obtained by taking G equal E. Nobody knew which was the value of the what will be called the Weinberg angle or the weak mixing angle. Okay, so you could have taken whatever you wanted for this coupling. So G equal E, G prime going to infinity gives the lower bound on the mass of the W, and G equal G prime equals square root of 2E gives the lower bound on the mass of the Z. I must say that this lower bound were not taken immediately seriously by several people working on the subject. And of course, the other major step, new step, is use of spontaneous symmetry breaking in generating fermion masses, as you see it from here. The Yukawa coupling of the X field with the fermions. In the paper, Weinberg asked, is this model renormalizable? He guesses that it could be the case, but of course, one had to wait the rigorous proof of Toft and Veltman that came a little time after. Now, of course, the other question that remained open at the end of the paper was how to include hadrons. And the inclusion of hadrons took place in between 70 and 73, with, first of all, the fundamental step that finally understood how to take care of neutral current, strangest change in neutral current. You see, it's pretty clear that the reason why quarks or hadrons were not included here is because of the fact that one really didn't know how to deal with the problem of neutral current, strange changes in neutral currents, because already several years earlier it was pretty clear that from bounds on this process or from the mass difference K0, K0 bar, to make sense of delta S equal 1 and delta S equal 2, one would have needed a cutoff of the effective Witch interaction pretty low, 2, 3 GeV, significantly lower than the number that I gave you for the masses of the W. And of course, the solution came with the observation of Glashow, Iliopoulos, and Maiani that the current, the Cabibbo current, which is this first piece, had to be completed with the inclusion of charm and the orthogonal combination of Strange and D. Okay. Then, of course, the major steps in the strong sector of the full theory, Gross, Wilczek, Politzer, asymptotic freedom observation, and not less importantly, Gell-Mann, Fritsch, Bardeen, Lloyd-Wheeler, that starts speaking of colored quarks coupled to an octet of gluons. Now, in front of this comes the Weinberg synthesis in a paper that is really worth reading. You know, that's the usual ability of Weinberg of putting everything together in a fully consistent theory, right? In a paragraph, in not more than a paragraph, he says, you know, the way to include into the theory that he had already written of SU2 cross U1, the strong interaction had to follow this path. The full group had to be the product of the group for the strong interaction times SU2 cross U1. The fermions had to form non-chiral reps of the strong group in such a way that respecting the strong group, the masses of the fermions could be given. And the third important feature is that scalars are GS neutral, so that the vacuum exploitation value of the scalar leave GS unbroken. And that's, as I think you understand, is the essence of the full story. In the paper, Weinbergs ask, again in his old typical style, another crucial question: why the weak interaction do not produce parity and strangeness violation of order alpha, not of order not of order GS, 1 over MW square, of order alpha? And the answer comes by simply writing down the most general dimension 4 up to dimension 4 Lagrangian for the effective strong interaction, where this Z could contain a gamma phi, where this M, which is a matrix, right? We are in flavor space even, there is strangeness included here, okay? So Z is a matrix, 1 plus a matrix times gamma phi in flavor space, including strangeness, and similarly for them. Now, this is the most general Lagrangian you can write down, and Weinberg notices that by psi redefinition, parity and strangeness are accidental symmetries of the strong and electromagnetic interactions, because by psi redefinitions, the gamma phi, you can get rid of the gamma phi. Anomalies are another subject, okay? So you see, I am at the end of the first part. I find useful to show this page, which emphasizes the synthetic character of particle physics. You can write down all of particle physics, provided you know the rules of the game, provided you know what field theory is. You can write down all of particle physics in one page by specifying the symmetry group, by specifying the particle content, how they transforms under the symmetry group, and by stating that all operators included in the Lagrangian have to be dimension less than or equal to 4. Now, of course, this page, which I repeat, I like it very much because it emphasizes the synthetic character of the standard model, does not put the theorists out of business, right? Because the theorists after that have to work a lot to get the consequences. And in fact, there's been very important research that is still going on and is still essential to give exact meaning to this page. But this is the synthetic description of the standard model. And I will come back to this issue of the synthesis of the standard model. Okay, so let me go to the second part. Briefly, right? Because it would take a series of lectures to describe all of the amazing success of the standard model. 1974 now, up to now. Well, of course, the first great discovery that put the standard model in business, the electroweak part of the standard model in business, was the discovery of neutral current. Weinberg, at the end of 71, wrote a paper in which he noticed that given the poor knowledge that he had at the time of the mixing angle, of the weak mixing angle, of the Weinberg angle, whatever you can call it, he put a lower bound and the upper bound on the neutral current versus charge current interaction of the neutrino. In fact, having to find at that time with a upper bound coming from CERN pretty close to this lower bound. So Weinberg was hoping that his theory was right, and he insisted on that. And in fact, at the end of 73, 74, the Gargamel, the bubble chamber operating at CERN, of which you see here the actual bubble chamber that you can see in the CERN. If you enter the CERN site, this is the result that was given for the neutral current to charge current ratio of the neutrino, consistent with this prediction. And in fact, this is an historical plot that you can find in the paper, in which you see the expectation depending on the mixing angle and the consistency of the result with the expectation. Now, of course, the other major success of the standard model is the progressive discoveries of all the expected particles. And here I have photographed the situation in 73 when all the ingredients of the standard model, that's why I indicate 73, right, as the end of the making period, right, were there, including CPV if three families, the observation of Kobayashi and Mascaro, right? Even though, the discussion on the gauge group, the discussion in particular on the origin of CP violation went on for all the 70s and even later, right? But it's true that all the ingredients that we now think are important in the standard model were known in 1973. And these were the particles known. All the dates are experimental dates, with the exception of the one in color. You understand why I put to 1905 for the photon. one can discuss the date at which quarks were, quote unquote, theoretically discovered. Of course, quarks were introduced earlier than that, but you know, at the beginning more as theoretical entities and so on and so forth. So roughly speaking, in the 60s, the quarks entered into the game. And here, of course, is the situation in 2012, where, you know, it is interesting to look at the dates. For those of you that don't know them, you see that the 70s have been very, very important and crucial, but, you know, even the other particles that have to wait for an explicit discovery. And they let you guess why I have put the stars here. Now, precision in QCD, well, just one slide. This is really remarkable. As you see here, the consistency fixed only by one parameter of all the measurements of the running strong coupling constant. That allows to fix the value of the alpha S2 at MZ with the precision that is better than 1%, as you see it from here. Now, why have I written here Sterman and Weinberg? Because you see, not all, but many of these entries here come from jets. And Sterman and Weinberg dictated the philosophy that then, you know, produced the continuous interaction between theorist and experimentalist, how to define jets in an optical way. But the basic observation is simple. Whenever you define an observable that is infrared free and has a typical momentum that is, say, above, say, 2 GeV, then you can compute it in perturbation theory without making any reference whatsoever to the Parton model or whatever, right? So that was the observation of Weinberg that has been instrumental in constructing this plot. Not less important is the electroweak sector. I suppose that many of you have seen this plot, which puts together all the observables essentially at the Z and at the W pole. But it's worth having a look at it. So you see there are 5 entries. The red entries are inputs, right, corresponding to the 5 parameters that are important in the standard model that you all recognize, I suppose. Then there are 3 green observables that are related to charge current, and then several observables related to neutral currents, the Z-pole observables, essentially, right? And the important thing is that each predicted observables in this fit is removed from the fit, right? So this is a real prediction. It's worth, I think, commenting again on the precision of the electroweak fit. This is a plot that many of you may have seen, but it's worth looking at it, right? So you see this blue ellipse, right, is the prediction of the mass of the W and the mass of the top using the electroweak observables that I have described before, compared with the direct measurement. And as you see, the level of consistency. Why this is important? You see, this is important because it is literally true, and I will even come back to this, that the standard model is not capable to predict the mass of the top and the mass of the W. Nevertheless, it is true that there are many observables that are correlated by this parameter, in particular, all of the electroweak fit correlated among themselves through these parameters, which meant that in 1994, before the discovery of the top mass could be essentially predicted, quote unquote, in this way, right? In this way. And in 2012, in fact, already at the end of lab, in the year 2000, the mass of the X could equally be predicted, right? Another way to see the impact of the electroweak interaction is by using these 2 effective parameters that are capable to catch all the electroweak corrections, the typical gauge corrections, loop gauge corrections, for all the Z-pole observables and the W-pole observables, not only in the standard model, in fact, but for any theory that is flavor symmetric and quark lepton symmetric. And this is what led, I think, the majority of us to think that at the end at lab, that the gauge sector of the standard model had been established. And this, I think, is important, and we'll come back in the following. The last plot that I want to, the slide that I want to show on the test of the standard model is this page, which I call the ultimate precision, which shows the comparison between theory and experiment in the G-2 of the electron, of the anomaly of the electron and the anomaly of the muon. Never mind the level of agreement at the moment. I will even say something later on this. The important thing to notice is that you see the level of comparison is the level of error. The error is the level of 1 part per billion here, and in the muon at the level of 1 part per million. And again, Jacques and Weinberg in 1974 were the first to compute the one loop weak correction to the G-2 of the muon. Now, I hope you will forgive me if I've included this sketch, but I put it there because it reminded me of the fact that I normally use a page like this when I give a talk to high school students about particle physics, because in fact I think that the collection of this page and the page about the synthetic nature of the standard model, to me, is the most synthetic way of presenting the power of the standard model in all its respects. Yes, here is again the issue of the synthetic nature of the particle physics. Once again, in a way that I am sure you are familiar with. Weinberg would say, as said, the world of physical phenomena reduced to a finite set of fundamental equation principles. That was his way of thinking in terms of reductionism, right? Now, these data, I think, are important. I told you already. The dates are the approximate dates of the experimental test of the various lines at different levels, right? This is the A sector, and as I told you, the end of lab showed that the basic structure was correct. The test of the X started with lab, essentially, right? And with the incredible importance of the discovery of the X, but I think that is still going on, as I will argue in a second. And of course, the flavor bit, right, with a construction that started with Cabibbo and so on and so forth. But in terms of tests, it seems to be that the key year is the year 2000, when at least one possible first year is the year 2000, when one first saw direct CP violation in the Keown system. For those of you who remember this notation, the epsilon prime over epsilon first observed to be different from zero, as expected in the standard model, first at CERN and then in the US, and again with the testing that goes on. All right. So, how much time do I have, Roberto?
So, how much time do you need?
5 minutes.
5 minutes. Okay.
Okay. Now, the future of the standard model. Is there a difference in the two sectors of the standard model? So, I am brief, right? Here, there is a little reordering of the gauge sector and the X sector for reasons that I have explained. the gauge coupling of the Higgs cannot be doubted. So this slight reorganization, right? And it is a fact that many of what can be considered problems in of the standard model are in the Higgs sector. The hierarchy problem, you all know what I mean. The cosmological constant problem, which you may say it's not really a problem for the standard model, but in fact, from an effective field theory point of view, they look very much the same, these two problems. And then the flavor problem, which means that the combination of this and this makes that no particle mass is calculable in the sense that I said, with the qualification that I said, there is no particle mass except for the photon and the gluon that is calculable in the standard model, which makes me think that this is a legitimate question. Can we tell for sure that we know the true nature of electroweak symmetry breaking? Of course, I agree, this is a pretty conservative question, yes, but in science to be conservative is meaningful, and maybe this is a question put forward by an old man, as I am, but I think that it makes sense. Also because, based on this comparison, here you see the calculation of the measurement of the various coupling of the Higgs, typical precision 5-20% against the precision in the electroweak test at the level of 1 per mil, okay? Which makes me think that this and the previous page make it that a Higgs factory is due to what? To the cultural evolution of mankind. Best, of course, if it's on the way to a high energy collider. This seems to me one important step that should be taken in the future if we want to really understand the true structure of the standard model. And we know the reasons would take a seminar. Even this page, you probably know, right? The problem of question for the standard model, the issue of neutrality of hydrogen, right? That cries for some sort of unification. And of course, here I underline again the contribution of Weinberg, who, together with G.G.I. Ellen Quinn, first showed how the evolution of the coupling constant could lead to unification. Of course, there are phenomena which are unaccounted for, we know. There is the issue of why there is apparently one single operator in the standard model, according to the rule that I have given before, that needs to be, that doesn't seem to be there. You know the story of actions, you know the contribution of Weinberg to that. Why only D less than or equal to 4 operators? Neutrino masses, proton forever. Weinberg made the full list of the operator in 1979, making a lot of important observations. And then, of course, lack of calculability, as I said already. Now, there are current anomalies in the test of the standard model, and this is a partial list, which, however, is not badly chosen, I think. Except for the mu on G-2, they all refer to semi-leptonic BDKs, charge and neutral. And you see that there is a consistent displacement of all the neutral current observables in semi-leptonic BDKs with respect to the prediction. As it is the case, although with a fewer number of observables in the case of the charge current. And we have all heard of the mu on G-2. Now, to comment on this is not really part of the talk, but there are general lessons to me, which are the following. In many cases, the theoretical prediction is definitely more precise than the experimental precision, which means that a precision program has to be followed in the coming years in flavor as in flavorless physics, right? This, I think, is a very important step for the next decade, say. If confirmed, and this is an important qualification in my view, but not the subject of this talk, the coherence of B-decay anomalies are suggestive of some approximate flavor symmetry that plays a role in understanding what's going on here. And also, independently, to me, the G-2 of the muon, in case it is confirmed, can be easily interpreted as a first sign of supersymmetry. Of course, if they are roses, they will flourish. Now, where is the scale of flavor? Of course, you see, if flavor is confined to high energy, then certainly all of these anomalies will have to go away. However, it makes a lot of sense to think that new physics in the multi-TV is hidden by a suitable approximate flavor symmetry. All right, let me finish by let me make Weinberg speak. Now, Weinberg was not only a great physicist, as it has been said, but it was also a great intellectual, which meant that he regularly published in the New York Review of Books, among many other interventions, public interventions, a series of articles, all very interesting to read. Here, November 7, 2012, the same year of the discovery of the Higgs, Weinberg writes an article whose title is Physics, What We Do and Don't Know. Now, I copy one paragraph towards the end. He says, even so, the Standard Model is clearly not the final theory. Its equation involve a score of numbers, like the masses of quarks, that have to be taken from experiment without our understanding why they are what they are. And you can go on. A few paragraphs later, he says, inflation is naturally chaotic, bubble form in the expanding universe, perhaps each with different values for what we usually call the constant of natures. Then he says, if this is true, then the hope of finding a rational explanation for the precise value of quark masses and other constants of the Standard Model that we observed in our Big Bang is doomed. We would have to content ourselves with a crude anthropic explanation of some aspect of the universe we see. And you can keep reading. You see, there seems to be a contradiction between these two statements, right? Isn't that the normal reaction? I don't think there isn't. In fact, look at the title of the paper, What We Do and Don't Know. The search goes on. Thank you very much. Sorry for having kept you a little bit too long, perhaps.
Thank you very much, Ricardo, for the great talk. Okay, so I think we can have now specific questions on your talk, if there is any, so people can raise their hands. I would really limit questions now to those on specific aspects of your talk. Otherwise, more general questions or comments can be asked at the end.
We have one in the chat.
Let me see. I have somehow lost the page. Let me.
Yeah, so I can read it for you if you want.
Thanks.
So Jay Harnard is asking, can the Standard Model be used to compute the proton-proton scattering amplitude? And can the Standard Model provide the range of the strong interactions? Strong interactions.
To compute the
proton scattering
proton cross section
and provide the range of the strong interactions.
Yeah, if you put together enough experimental information with the essence of the Standard Model, you can, sure. Why not? You have to put together enough experimental information in a range in which the Standard Model suffers from the fact that the strong interaction part of it in the low Q momenta is not straightforward to analyze, but very much in the same way. But you can certainly end up with a prediction for proton collision and the range of the strong interaction. Yes, I have shown you, I don't know if you see my screen. Do you see my screen again?
We do.
Yes.
We do.
Yes.
So you may remember this page, right? Or this page. This page tells you that, you know, at lambda equal, what, 200 MeV, the coupling constant explodes and you have to deal with the problem, yes. I don't know if you refer to the fact that we are still waiting for a solution of the how's it called? The solution of the confinement problem and things like that. Of course, you know, there are always problems. You know, if a physical theory is a good theory, there are always problems to be solved. But we should not be afraid of that. As I say, the story of the standard model is not over. I hope I was able to answer the question.
I see that there are other questions in the chat, but probably most of them can be postponed to the discussion session, I think. So I would continue with our next speaker, and that would make us on time, and then ask for more questions at the end. So thanks a lot, Ricardo, again, for your very nice talk. Our next speaker is Howard GGI. Howard, are you here? Okay, I can see you. You're muted, but I can see you. So let me give you a very short introduction. So Howard GGI is the Mallinckrodt Professor of Physics and Harvard College Professor at Harvard University. He made, of course, very important contributions, everybody know. And among them, I would like to mention just his work on grand unification, work on composite models that I love, effective field theories, his contributions to effective field theories, especially applied in particular to QCD. And of course, everybody knows you for your fantastic books on weak interactions and Lie algebras. So the title of the talk is Effective Field Theories and the Low Energy Limit of Strong Interactions. Please.
Okay. All right. Thank you very much. It's wonderful to be here, at least virtually. There are different ways of interpreting the title of my talk, depending upon how tightly one wants to tie effective field theories to the low energy limit of strong interactions, and exactly what one means by low energy. Altogether, it's way too big a subject, and I'm just going to pick and choose a few areas that I'm most curious about and that bear the imprint of Steve's unique style. There are few physics papers that I read for pleasure every few years. One of these is Steve's papers on phenomenological Lagrangians for the Schwinger-Festschrift in 1979. And I can't resist showing a few quotations from the paper. The bold is mine. Right at the beginning, I discovered that Steve had visited Harvard and talked to Schwinger in 1966 while I was an undergraduate, probably while I was taking Schwinger's course on source theory. At this point, what Steve means by a phenomenological Lagrangian is one in which the interaction terms are used only in first order. Having only derivative interactions is crucial because it means that in the chiral limit with massless pions, as the pion energy goes to zero, the amplitude goes to zero unless the derivative is compensated by a pole on an external line. One of the clumsinesses that Weinberg refers to here is the starting point. He starts from the old linear sigma model of Gell-Mann and Levy, which has the right symmetry, but it is otherwise not particularly well motivated and Steve had to compensate by putting in the physical normalization of the axial vector current by hand. The other clumsiness is that the symmetry structure is only approximately right. But at least to first order in the pion fields, the pion couplings vanish except for derivative terms, which was the crucial thing. Now here's the fun part. Again, the bold is mine. I don't know whether Schwinger already knew about the clever mathematical trick of induced representations that he suggested that Weinberg use, or whether he invented it independently. But the idea is this. To build an induced representation of the chiral symmetry, you construct a chiral transformation on the matter fields as an ordinary isospin transformation by an angle that depends on the pion fields. And then you find a nonlinear transformation of the pion fields that reproduces the full chiral algebra. The chiral transformation is said to be induced from the isospin transformation by the nonlinear transformation of the pion fields. And this can be applied to any isospin representation. So the isospin transformation is then local, depending on position, because it depends on the pion fields, which depend on position. But because the pion fields appear only in the angles of the isospin transformation, they disappear completely to all orders from any isospin invariant term without derivatives. The Lagrangian depends on the isospin of the matter fields without any assumptions about what SU2 cross SU2 representation they are part of. Physically, this means that it's simply meaningless to ask about the chiral transformation properties of the matter fields themselves. And now to all orders, the pion couplings all involve derivatives or explicit symmetry breaking terms. One of the many things that I love about Weinberg's paper is the deft way that he handles Schwinger's source theory, paying homage to Schwinger without noting that Schwinger was not really doing anything interesting at this time. And while it's certainly true that many physicists had pieces of the puzzle that Weinberg completed in this paper, Weinberg deserves credit for expressing the idea so clearly and in such generality. As Ricardo mentioned, generality is Steve's specialty. But why is this the right thing to do? The paper contains a very clear statement of one of the central dogmas of effective field theory, that field theory by itself has no content beyond Lorentz invariance and quantum mechanics. Perhaps Nima will amend this for us later today. But the key point here is that the new idea is that the momentum expansion can explain in what sense non-renormalizable quantum field theories make sense. The momentum expansion is an expansion in powers of the energy, and in this case, the symmetry breaking parameters, and it replaces and systematizes the notion of smoothness of amplitudes that was used in the old current algebra calculations. This is what is referred to as chiral perturbation theory. But more generally, Steve realized that the momentum expansion is the key to doing reliable calculations in renormalizable theories, including quantum loops. Even though there are an infinite number of parameters and an infinite number of counterterms required, only a finite number of them are required to calculate to a specific precision at a specific energy. And when coupled with the momentum expansion, Weinberg's Folk theorem about quantum field theory becomes a powerful tool that incorporates information beyond traditional perturbation theory. So the first thing I want to talk about is, where did this paper come from? It's so wonderful. I want to spend a good part of my talk discussing the history that led up to this beautiful synthesis. One possible source for this history is Weinberg himself. This is one of many papers written about that history. It's the opening talk at a conference celebrating the 30th anniversary of his Schwinger-Festschrift paper. And there are many similar talks. Here is Weinberg's summary of the progression. The starting point, of course, was Nambu, spontaneously broken symmetry, and so-called partially conserved axial currents. And Steve describes the progression from Nambu and PCAC through the early work on current algebra to his nonlinear chiral Lagrangian that allows current algebra calculations to be done more easily. And then he suggests that he lost interest until the late 70s, when he was inspired by Wilson's work on scaling in condensed matter physics and his attempts to justify quantum field theory to his students. It's a good story, and he writes beautifully as always, but it didn't convince me. I think there's some very important influences that are left out, and I wanted to dig into the history a bit, and this talk gave me a good excuse to do that. Nambu's PCAC did not catch on immediately. You can see that in the citations to Nambu's paper as a function of year. Initially, physicists just struggled to understand the physics of the Goldstone theorem, the connection between spontaneously broken continuous symmetries and massless particles in relativistic theories. Steve's paper with Goldstone and Salam, which Ricardo mentioned, was one of many examples, though of course it was a particularly clear and general treatment. But after the success of Gell-Mann-Neyman's eightfold way and the Cabibbo angle, the game heated up, and there was explicit discussion of the chiral SU2 cross SU2 and SU3 cross SU3 symmetries, and many applications that depended on the commutator structure. Steve, as usual, considered a very general situation and worked out the current algebra of an arbitrary number of pions. Even Steve thought that this was complicated. This is a typical page from this paper. But one beautiful thing that came out of this complicated mess was Steve's calculation of low-energy pi-pi scattering. This calculation gets to the heart of the non-abelian Goldstone theorem, and it can be understood very simply classically. A Goldstone boson wave packet is a local twist in the vacuum. And at low energies, the interactions go to zero because the packets look very much like the vacuum everywhere, but like slightly different vacua in different places. So, for example, two pi0 wave packets don't scatter from one another because all of the twists of the vacuum are about the same isospin axis, and they commute with one another. So the passing pions can twist and untwist the vacuum, leaving nothing behind. But a pi0 and a pi plus correspond to twists in different isospin directions, and the twists don't commute. So now the system is complicated in the overlap region, where one pion twists the vacuum and the other twists it in a different direction before the first one can untwist it. This leaves behind a little region of space with the vacuum twisted in the direction of the commutator, and this spreads to become the scattered fields. And that's the classical Goldstone boson physics behind Steve's pi-pi scattering calculation. The next thing that happened was that, according to Steve, he was sitting in a cafe in Harvard Square when he realized that he could find a Lagrangian that, when used in lowest order, would reproduce the effects of current algebra in a much simpler way. This was the clumsy approach that I discussed at the beginning of the talk. So finally, in 1967, Steve follows Schwinger's suggestion and constructs a fully invariant nonlinear theory using the mathematical technique of induced representations. So then there's a break. He says that only after a break of nearly 10 years to construct a standard model was he motivated by condensed matter physics and by his teaching to think again about the problem, and then finally tamed the infinite number of parameters and realized that non-renormalizable theories are perfectly renormalizable, and the momentum expansion allows one to calculate with them. At that point, he replaces the old-fashioned constraints of renormalizability by constraints on the sizes of non-renormalizable terms in the effective field theory. And this modern picture of effective field theory is born. So Steve's account makes a really good story, but I think it leaves out many important developments that almost certainly influenced his thinking, and I want to show you why I think so. These include maths-independent renormalization schemes, GUTS, effective theories of the weak interactions, heavy quarks, and perhaps most importantly, the U1 problem. So it's certainly true that Steve was doing other things besides thinking about pions in this period. But not immediately. This was a depressing time for quantum field theory. Weinberg's model of leptons paper did not make a big splash when it first appeared. I was just a baby at the time, but I remember seeing it when it arrived in my mailbox, and like most everyone else, including, I think, Steve himself, I ignored it because it didn't look renormalizable to me, and I didn't really know how to make precise sense of it. This shows up spectacularly in the plot of the citations to Steve's paper by year. There was equally little excitement when Glasgow and Iliopoulos and Miami figured out why a charm quark had to exist to explain the absence of neutral current effects that change flavor. I must say the statement of the Jim mechanism is very simple. If there are 4 quarks and they come in 2 complete families, each with identical weak charges, the strong interactions have an approximate SU4 flavor symmetry, and flavor changing neutral current effects are proportional to the SU4 symmetry breaking and can be adequately suppressed if the symmetry breaking is small. I think this is one of the most brilliant and annoying developments ever in particle theory. The reason that I think it's so annoying is that it implies that we have absolutely no idea what flavor really is. And as Ricardo mentioned, in the standard model, that turns out to be true. At any rate, these frustrations ended spectacularly in 1971 after Toft figured out how to make sense of spontaneously broken non-abelian gauge theories in general, and Weinberg's model of leptons in particular. This obviously is the reason for the jump in citations to the Weinberg and Jim papers, and also to the resurgence of quantum field theory in general. Toft's work opened up a new region in the map of quantum field theories, and some of us started exploring it by building models, both to see what was possible in this new class of renormalizable models and to try to find the right model. So I will discuss one completely crazy model building exercise in detail. James Byrkane, BJ, did something crazy that was both wrong and important. He came up with a numerological relation for the ratio of the muon mass to the electron mass. And he argued, and as far as I know, this is not published, that the relation was correct up to just at the level that one would expect if there were radiative corrections. it's right up to order alpha squared. Now, in hindsight, this seems completely ridiculous. But you have to remember that at this time in 1972, there was no tau lepton, and we weren't quite sure what to think about quarks. For many quantum field theorists, quarks were still a shorthand for symmetry properties of the still mysterious strong interactions. That situation would change like dreams over the next couple of years. But in early 1972, it seemed entirely reasonable to construct models in which mu over me is calculable. At this time, Steve Weinberg was still at MIT, and he got interested in the same problem. So we had a little contest between Shelley and me at one end of Cambridge and Steve at the other to see who could compute the muon-electron mass ratio. Although I think Shelley and I came closer to the goal, Steve made theoretical contributions that were much more important. He wrote a paper which described a model of leptons, his second and much less well-known than the first. It was based on SU3 cross SU3. And he reasoned that in this model, after symmetry breaking, there would exist Feynman graphs like the one shown here that might give BJ's formula. This is a brilliant wrong paper. Steve's model doesn't give anything like BJ's formula. He missed a counter term, and the electron mass is actually infinite. Shelley and I showed this and understood how to fix it by adding another SU3, but the solution was boring because instead of the square root of 2 in BJ's formula, we got a complicated ratio of heavy vector boson masses. And if we knew all the masses, we'd have a relation, but that didn't seem like much. The really interesting thing about Steve's model is that it is a kind of proto-gut. The gut-like properties can be seen in a simpler model with only one SU3, with both triplets transforming as threes. The point is that unlike SU2 cross U1, but like all gut models, this SU3 model has gauge interactions that we haven't seen. In this case, the right-handed weak interactions involving the top and the bottom components of the triplets. And also weird doubly charged currents involving the bottom two. To get rid of them, Steve invoked what he called super strong symmetry breaking. He added an octet scalar field with a vacuum expectation value in the lambda 8 direction and gave it a big vacuum expectation value. That breaks the SU3 gauge group down to SU2 cross U1, as we all know from Bellman's SU3. But in this case, it's used in a completely different way to give a large mass to all of the unwanted gauge bosons in this model. So these super heavy gauge bosons were constrained more by their virtual effects than by direct bounds on production. At this point, Steve was certainly not thinking about what are now called gut masses. In those days, a few or 10 times the W mass would have been plenty to suppress the unwanted interactions to an acceptable level. Needless to say, at the time, it was a pretty radical concept because we all still thought of the W and the Z as extremely heavy. To invent things that were heavier still was a bizarre act of genius. Because there's only one coupling constant in the model, the weak mixing angle is also predicted. And it's predicted to be a quarter, which at the time didn't seem very good, but now seems great. But of course, he was ignoring renormalization effects because nobody was thinking about at this time, because nobody was thinking about really large mass ratios. It's the fraction in this case, ignoring renormalization. The weak mixing angle is just the fraction of the total charge in the group invariant sense that comes from the SU2 gauge coupling right up here. Steve, as he was wont to do, generalized the question. He generalized the issue of BJ's relation into something much more interesting by expressing what we'd done in a symmetry language. What we found was a model in which the most general normalizable Lagrangian had no mass term for the electron, so that the kinetic energy terms had a chiral symmetry. But the full Lagrangian did not have a chiral symmetry for the electron field, so that the electron gets a mass due to radiative corrections, and the mass is finite and calculable because there's no counterterm to absorb the infinite contribution. Steve recognized that this sort of thing happens frequently in non-abelian gauge theories and suggested that it might be an explanation for some of the approximate symmetries we see in the world. The issue may require a little explanation. Symmetry, both gauge and global, played an important role in renormalizability from the very beginning. But nowadays, exact global internal symmetries have a bad name in quantum field theory, and we suspect that there may not be any at all. But approximate global symmetries are an obvious and important feature of nature. We knew how to use them by simply assuming that the Lagrangian of the world has a symmetry conserving part that is somehow large and a symmetry breaking part that is somehow small. But this might seem a little artificial if the symmetry breaking small part was governed by a parameter that was in some sense infinite and required renormalization. Steve realized that there were examples of QFTs in which the symmetry breaking term, like our chiral symmetry breaking electron mass, is finite and calculable in terms of other parameters because it's not present in the most general renormalizable theory, and therefore no counterterm exists to absorb an infinity. I think that Steve invented the name accidental symmetry for this situation, and I'm almost certain that I heard the name from him. It appears in a footnote in his paper on the subject. In our solution to BJ's challenge, the chiral symmetry of the electron kinetic energy term is an accidental symmetry. It's an automatic consequence of the constraint of renormalizability. But the problem with these models was that they could not accommodate fractionally charged quarks. And evidence for these from deep inelastic scattering had been piling up. And by this time, it was getting pretty convincing. So after years of experimental results, which were very interesting, but not easily theoretically interpretable, the deep inelastic scattering from SLAC was beginning to make sense and beginning to look like really interesting, though still confusing, quantum field theory. Another interesting thing that happened in this time was that Bouchiat, Iliopoulos, and Mayer, and Gross and Jakif reminded us that the existence of triangle anomalies put interesting constraints on these models. And Bim noticed that 3 colors of quarks was the right number to cancel anomalies in the electroweak model. So this fit very nicely with the original suggestion of 3 colors from baryon spectroscopy. So after the discovery of weak neutral currents, the basic structure of the electroweak interactions was pretty clear, but the nature of the strong force and the full significance of color was still not obvious. Of course, a big part of the push for quarks came from dimensional transmutation and asymptotic freedom. Dimensional transmutation was described by Sidney Coleman and Eric Weinberg in another of my favorite physics papers, Radiative Corrections as the Origin of Spontaneous Symmetry Breaking. The subject is a version of Weinberg's model that I think is pretty uninteresting, but the paper is a how-to-do-it manual of useful techniques in quantum field theory. The renormalization group, the loop expansion, the effective potential, and much more, written in Coleman's best pedagogical style. Almost in passing, they show how renormalization can convert a dimensionless coupling constant into a dimensional energy scale, characterizing the interaction. I didn't realize at first how important this was going to be. The history of asymptotic freedom is complicated, and I'm not going to get into it except to say that I spent a lot of my time during and after 1973 trying to do useful physics with it. At first, though, we were still assuming that we had to break the color symmetry and not yet recognizing the full power of dimensional transmutation. The recognition that color symmetry could be unbroken and the quarks confined developed gradually to many people over that year. And I first heard it from Steve in this paper. This indeed shows that Steve was thinking hard about current algebra even during the exciting time when we were building the standard model. And the paper also contains the speculations about what we now call quark confinement. And that idea was very important to me personally because it got me and Shelley thinking about unifying SU3 along with SU2 cross U1. So I've told the story of the evening that I found SO10 and SU5 guts elsewhere, so I'll skim over it almost instantaneously. But I started by thinking about the Pati-Salam SU2 cross SU2 cross SU4 model. This is a beautiful model, or almost a beautiful model. They discovered something very beautiful and then ruined it. They were probably the first to write down a model with charge quantization that could incorporate fractionally charged quarks. And in fact, Braun-Pais tells me that, ironically, they may have been the first people to write down the full gauge structure of the standard model, which is contained within their model. And I say that this is ironic because having written down the beautiful gauge structure that could explain fractionally charged quarks, they proceeded to do something absolutely gross to it. They spontaneously broke the color SU3 and the electroweak down U1 down to a subgroup that left the quarks with integral on-number charges. When we finally understood that it might not be necessary to break color SU3 symmetry at all, and that the massless gluons might be confined, it was easy to turn this into something more interesting. And basically, the first day that Shelley and I started thinking about guts, we thought about it during the day and didn't get anywhere. And then I went home and worked out the structure of the SO10 and SU5 theories in one evening. The idea was you start with Pati-Salam and get rid of the ugly symmetry breaking. And then you can immediately realize that the SU4 cross SU2 cross SU2 has an algebra that's equivalent to the algebra of rotation groups, SO6 cross SO4. So any idiot would think of combining these into SO10. And the interesting part was that I didn't have to think about what representation to look at. The spinor representation was the unique choice. So the group theory put the quarks and the leptons and the antiquarks all together for me into a single representation. That was something that Shelley and I had been unwilling to do, and that's why we weren't getting anywhere. In the Pati-Salam model, getting rid of the right-handed neutrino broke the symmetry down to SU3 cross SU2 cross U1, and I asked myself what subgroup of SO10 remained after I got rid of the right-handed neutrino. And eventually I saw that it had to be SU5, and then I could do all of the familiar calculations. And get the weak mixing angle and everything else. I now looked at the extra gauge bosons. That had been, I'd avoided that in SO10 because it was complicated, but in SU5 it was easy. And I drew the relevant diagram, which was clear that it would produce proton decay, and I was devastated. I went to bed. I knew the proton was stable. But Shelley, when I told him about it the next morning, was more excited about proton decay than anything else, and he was right, of course. We went up to the library and looked up the bounds and found that our super heavy gauge boson using Steve Weinberg's mechanism of super strong symmetry breaking had to be greater than 10 to the 14th GeV. We wrote the paper and went on to other things. I stupidly didn't include SO10 in a footnote, which gave Fritsch and Minkowski the opportunity to find it independently later on. In the next few years, I wrote only 2 papers on guts. One was a conference report about SO10, but the interesting paper for this conference was the George I. Quinn Weinberg paper, in which we computed the renormalizations of the couplings in guts and predicted the proton lifetime. The problem that GQW solved was that the then conventional picture of mass in dependent physical renormalization was very inconvenient in a theory like SU5, with very different physics at very different scales. In principle, a mass-dependent physical renormalization should allow you to evolve couplings from the gut scales to low energies and see the coupling splitting. But in practice, it was a hideous mess. So the key idea was that below the scale of the breaking of the gut symmetry, the leading logarithmic renormalization effects were just what we could calculate in an SU3 cross SU2 cross U1 model, and the unification could be put in simply as a boundary condition at the gut scale. We justified this by appealing to the Appelquist-Carrizone theorem and using different mass-independent renormalization schemes in different energy regions. This was a modern effective field theory calculation, although we did not describe it that way at the time. The couplings in the different regions evolved differently and were connected by matching at the symmetry breaking scale. This was a departure from the conventional view of renormalization as relating directly to physically measurable properties. It fit nicely with the 't-Hooft-Veltman scheme of dimensional regularization and minimal subtraction, but only if we supplemented it by an effective field theory idea of different theories in different regions. And that idea is, in fact, absolutely required to make minimal subtraction useful in any theory with multiple energy scales. I don't have much use for anthropic arguments, but I am enormously grateful to have been born into a universe in which God had chosen the parameters to illustrate almost every possible interesting theoretical idea relative to the standard model. And heavy quarks are a great example of that. Because I'm running out of time, I'll skip over the details here, but basically the parton model was really confusing initially, because some parts worked great for the deep inelastic electron scattering, but it failed badly for E plus E minus. And when many of us were convinced because we tried everything else, that charm had to exist, and that the problem with E plus E minus, the E plus E minus parton model, was that charm was being produced. Now, as the J-psi was being discovered at SLAC, Bert Richter was actually a Loeb lecturer at Harvard, giving lectures on his theory that the rising R that they saw at SLAC was due to the fact that the electron was a hadron some fraction of the time. And at a lunch for Bert in the department, David Politzer and Tom Appelquist suggested that they look for narrow peaks in the data. And of course, Bert ignored that. The announcement of the J-psi occurred a bit shortly thereafter. it was actually surprising how long it took to actually see charm. But eventually, it's useful to remember that half of the explanations of the Japes I in the famous PRL after the discovery were silly, even things by very famous people like Schwinger. But it ended happily. Charm was eventually discovered exactly where we said it should be. R in E plus E minus was starting to look exactly like Appelquist and Palliser said it should. Except, of course, in the meantime, God had thrown us an extra heavy lepton. And in the space of less than a decade, we'd gone from confusion to confidence. And quantum field theory was ascendant. But the interesting point for Weinberg was that we had several new energy scales above a GeV. Certainly the charm mass and the W and Z mass, and plausibly a gut scale. And we could no longer ignore the effects of running between these scales. It was becoming obvious that some version of effective field theory was the way to deal with this. And the question was, how does it work in detail? All of this was in the air, and I just don't believe it did not have an effect on Steve's thinking. As far as I know, one of the first people to really figure out the details was my office mate in the late 70s, Ed Witten. And while his calculations are not exactly described in the same language that Steve uses, all of the pieces are there. The last piece I wanted to mention is the U1 problem. Classically, the symmetry of three massless quarks has an extra chiral U1, and it is a disaster. Nothing would work. It was when the quarks were not real and were just you just used them to abstract symmetry properties, you could ignore that problem. But that was no longer true, as now that the reality of the quarks had become more or less established. In fact, there's a smoking gun here that shows that Steve was thinking about these issues in 1975 during this period where he says he wasn't really thinking about it. This is a delightful little paper. It shows that changing the decay constant of the U1 current can't help very much. So if anyone was not confused already, this paper would certainly have gotten their attention. But in fact, most people were already confused. And one reason I think that people weren't trying harder to sharpen the tool of chiral perturbation theory was that it seemed it didn't work and that something important was missing. And again, 't Hooft came to the rescue. After 't Hooft's paper, there was no reason not to dive back into chiral perturbation theory and really make sense of it. And that's what Steve did. I want to say just a few words in the few minutes I have left about after phenomenological Lagrangians. But my main message is that everybody should go back and read this paper. It's just so beautiful. So the legacy of phenomenological Lagrangians goes in many different directions. And many of the most solid and convincing of these go through Baird. I still remember a seminar by Harry Leutwiler over 30 years ago talking about the program that he and his colleagues had established to push the phenomenological Lagrangian program further. Harry described their superb work testing the theory, and then he compared chiral effective field theory to an appliance manufacturer and with some revolutionary patents. And he said in his talk, he said something like, if you like the refrigerator I just showed you, I have a washing machine and a microwave to sell you. He was referring to the fact that they could use the same technology, not just in particle scattering, but in lattice QCD, in QCD at finite temperature and pressure, in QCD in a finite box, etc., etc. It's a beautiful collection of applications. Finally, citations can be an unreliable tool but because I don't have time or the expertise to discuss all of the many descendants of Steve's work on effective field theory, I've just listed some research papers, not review papers, just new research that refers to Steve's phenomenological Lagrangians paper, and which themselves have generated more than 500 citations. Just the titles here show a remarkable story of how far and how widely Steve's ideas have spread. And this doesn't include many influential works that involve effective field theory but don't involve the chiral symmetry, but they still have their roots in Steve's ideas. So it's an absolutely remarkable legacy. And he was a remarkable physicist. And thank you for encouraging me to look into this history a little bit.
Thank you. Thank you very much, Howard, for your very nice talk. So there is time for a few questions on your talk. If there is anybody, he or she can raise a hand. Okay, I don't see any question. I don't see any hand. So I thank you again. And at this point, we have a break, a very short break. So 20 minutes, everybody can rest. And then we reconvene at 5:10 p.m. Central European time. So in 20 minutes from now. Thank you.
There is a discussion going on the chat.
I just tried to answer the question about PP scattering.
Yeah.
If you stipulated unlimited computing power, there'd be no trouble to calculate PP scattering with a classical computer. More realistically, you might need a quantum computer because of the real-time nature of the process.
We are about to start again.
So shall I share my screen then?
Yes,
Yeah.
Enrico
Yes. Okay, so
we'll share the session.
yeah, let's start the second part.
Okay.
And our next speaker is the Charles Simoni Professor at the Institute for Advanced Study, Edward Witten. So you can start, and you have 40 minutes plus 10 for questions. Thank you.
Thanks very much for the invitation, and thanks as well to the organizers for putting this session together and for inviting me to speak. I've certainly enjoyed the first two talks. So the title that was suggested was about Weinberg and the role and meaning of symmetries in physics. I've slightly altered the title. And so this topic is extremely broad, as there were so many facets to Steve Weinberg's contributions to understanding the role of symmetries in physics. So I tried to make a list of highlights, most of which we've heard at least a little bit about from the first two talks. There was his early interest in spontaneously broken global symmetry, with several proofs of Goldstone's theorem, or as they called it, Goldstone's conjecture, with Goldstone and Salam. There were low energy theorems for soft gravitons and photons, and the relation of these to gauge invariance and general, the relation between assuming that a photon or graviton doesn't decouple at low momentum and a requirement of gauge invariance or general covariance in its couplings. Then there was current algebra and effective field theory, spontaneously broken symmetry in the hadronic world, spontaneously broken gauge symmetry and the standard model, approximate global symmetry as an accidental consequence of gauge symmetry, and effective field theory as the central truth of modern physics. So, well, those are at least 6 main topics in Steve's work on the significance and role of symmetries in physics. And we didn't hear much about the second one in the first two talks, but the first two speakers said a fair amount about most of the other 5 topics here. So my own most vivid personal recollections of Weinberg have to do with learning about current algebra and effective field theory from Weinberg. So I came to Harvard as a postdoc in the fall of 1976. So Weinberg had called me up to make the offer. I accepted on the phone, which seemed to surprise him slightly. When I was at Harvard, we used to have weekly family meetings. And so somebody would make a presentation about something of current interest. But if something came up in those discussions that Weinberg thought other people didn't understand, he'd make a little lecture about his understanding of it. And current algebra was clearly a subject which he was dissatisfied with how well people understood it, because he would regularly give a short lecture on his understanding of current algebra. I was one of the physicists who didn't understand current algebra when I came to Harvard. I'd been exposed to the traditional way that soft Plian theorems were deduced by manipulating currents and various clever arguments, but it seemed like hocus pocus. So I was one of the targets for Weinberg's lectures in current algebra, and the way I personally learned about soft Plians and effective field theory and hadronic physics was from the lectures he used the informal talks he would give at his the family meetings whenever current algebra came up. Now, I spent part of the weekend rereading some of Steve's most classic papers on the role and meaning of symmetries, trying to think about the best way to approach this lecture. And, well, it's a strange experience because often your reaction when you read something is, but everyone knows that. Then you have to pinch yourself and realize that this paper is why everyone knows that, or where everyone knows it from. So one option for the talk was to organize it around highlights of some of the classic papers. But many of them are well known, and I suspected some of the most important would figure in other lectures this afternoon, or morning if you're in the East Coast of the US. So I decided it would be more fun to organize the talk around some of the lectures and articles in which Steve explained the evolution of his own thinking about physics. And I picked three that were spread out in time. So first was the Nobel Prize acceptance speech in 1979. Then an article almost 2 decades later, what is quantum field theory and what did we think it is? And then after another 2 decades, half a century of the Standard Model. So we'll look at those three talks and how he explains how his thinking evolved up till that point. And we'll see that there's a sharp change between his outlook in the first one and in the last two, which is in a sense, a more modest view of what we understand and a description of everything in terms of effective field theory. A main theme in the last two is that whatever we've done should be understood as an effective field theory. So that was kind of explained in Howard's lecture. So the first of the three of Steve's lectures and articles that we'll look at closely is the Nobel Prize acceptance speech from 1979. So a main theme of this lecture is that there were two central organizing principles, as Steve sees it, in the development of the Standard Model, which were symmetries and renormalizability. So he writes, to a remarkable degree, our present theories of elementary particle interactions can be understood deductively as a consequence of symmetry principles and a principle of renormalizability that's invoked to deal with the infinities. After 1905, with special relativity as a precedent, physicists viewed symmetries as practically sacred. Symmetry principles took on a character of universal principles, expressions of the simplicity of nature at the deepest level. So Steve explains that then it was very difficult to become accustomed to imperfect and partial symmetries. So isospin is an imperfect and partial symmetry. It's not a perfect symmetry. It's really only a symmetry of strong interactions. And later, there were other imperfect and partial symmetries like strangeness. So Steve says it was painfully difficult to become accustomed to imperfect and partial symmetries. And later, there were shocks of learning that some of the supposedly perfect symmetries were actually imperfect. P and CP were both violated. So nature was not as perfect as assumed. Well, why was it so hard to accept the idea of symmetries that are only approximate or only apply to some interactions? Steve writes, if symmetry principles are an expression of the simplicity of nature at the deepest level, how can there be such a thing as an approximate symmetry? Is nature only approximately simple? Well, a turning point, so this is the background to the impact on him of the idea of spontaneously broken global symmetry, which he learned about from the work of Goldstone and others, such as Nambu. After learning of the idea of spontaneous breaking of symmetry, Steve writes, as theorists sometimes do, I fell in love with this idea, but as often happens with love affairs, at first I was rather confused about the implications. So first of all, why was Steve so excited about spontaneous symmetry breaking? Well, he was troubled, as he writes, about the approximate and imperfect symmetries, and he hoped to promote the approximate and imperfect symmetries to exact a priori symmetry principles, where the imperfections were brought about by spontaneous symmetry breaking. It was therefore rather disturbing to hear of a result of Goldstone showing that exact spontaneously broken continuous symmetry implies the existence of a Goldstone boson. So Steve became extremely interested in this result, and one of his important early papers that you've heard about already in this session with Goldstone and Salam consisted of 3 proofs of Goldstone's theorem. We call it Goldstone's theorem, but they describe it as Goldstone's conjecture, for which they gave 3 proofs. At the time, Weinberg's conclusion was that spontaneous symmetry breaking is not a useful idea for fundamental physics, because in nature there weren't any Goldstone bosons. Goldstone bosons, at least in the strong interactions, would already have been discovered. And he explains that he tried to add a epilogue to their article, which would have quoted Shakespeare expressing a lament that spontaneous symmetry breaking is a useless thought, but the editors censored it. The editors of Physical Review didn't allow that to go into print. Now, Peter Higgs and others showed by about 1964, following ideas that came from condensed matter through Phil Anderson, and also ultimately going back to Julian Schwinger's paper on the Schwinger model, they showed that spontaneously broken continuous gauge symmetry does not lead to existence of a Goldstone particle. Here the emphasis is on the word gauge. So Goldstone's theorem was for spontaneously broken global symmetry. Higgs and others showed that for spontaneously broken gauge symmetry, there's no Goldstone particle. But Weinberg writes, physicists who heard about this, but I've added the word particle because, of course, it wasn't regarded as a technicality by people who knew about superconductivity. But anyway, particle physicists who heard about this generally regarded it as a technicality. And it may have not attracted so much attention because of a new development, the Adler-Weisberger sum rule, which in Weinberg's telling turned Goldstone bosons from unwanted intruders to welcome friends. So the idea of the Pi-ionized Goldstone boson of a spontaneously broken approximate chiral symmetry is earlier. It goes back to work of Nambu and others around 1960. But it was the Adler-Weisberger, I left out the ER, sum rule that got Steve really excited about current algebra. I often heard him, both at those family meetings I mentioned before and later, say that this sum rule got quantum field theory back on track after years in the doldrums. So the original formulation was different, but Steve reinterpreted the Adler-Weisberger sum rule as a current algebra formula for low-energy pi nucleon scattering, combined with a more general dispersion relation that was already previously known. And as you've already heard from the last talk by Howard, he spent much of the years, starting in '65, working on current algebra and reformulating it in terms of effective field theory. He introduced effective field theory as a tool that makes it straightforward to calculate the consequences of spontaneously broken exact or approximate global symmetry. That was enormously influential at multiple levels. First, it made current algebra transparent, and it was a prototype for thinking about other aspects of physics. As I'll explain later, Steve came to view it as the central organizing principle of our understanding of physics, effective field theory. But just for current algebra, I don't even know if young physicists today learn how current algebra was done before effective field theory was introduced as a tool. There were clever arguments about endpoint functions of currents, low energy behavior of amplitudes, and a little bit of hocus pocus. So the current algebra approach was so much more transparent and simple to use and to generalize to higher orders that the older approaches really went into eclipse. So as I said, I as a graduate student learned the older approaches, but I don't know if at what point younger physicists, or until when younger physicists have done so. The other strain of thinking that went into the standard model was renormalizability. So as Steve tells, a lot of physicists had viewed renormalization of divergences as sweeping problems under a rug. But Weinberg's view was different. Here's what he writes in his Nobel Prize acceptance speech. I learned about renormalization theory as a graduate student, mostly by reading Dyson's papers. From the beginning, it seemed to me to be a wonderful thing that very few quantum field theories are renormalizable. Limitations of this sort are, after all, what we want, not mathematical methods which can make sense of an infinite number of physically irrelevant theories. I thought renormalizability might be the key criterion, which also in a more general context would impose a precise kind of simplicity on our theories and help us pick out the one true physical theory out of the infinite variety of conceivable quantum field theories. Well, soon after getting his PhD, Weinberg proved a relatively difficult theorem, Weinberg's theorem, probably his most significant result before the paper with Goldstone and Salam, although perhaps I'm overlooking something, that in a sense completed the proof of renormalization theory. He proved something that the founders had probably in generality assumed, which was that if you have a Feynman diagram, which overall is convergent by power counting, and all its subdiagrams are also convergent by power counting, then the diagram is actually convergent. Well, jumping back to 1967, jumping ahead to 67, by 67, Weinberg was trying to make a gauge theory of the strong interactions. He wanted to turn chiral symmetry into a spontaneously broken gauge symmetry with the rho and A1 as gauge bosons. Well, one thing you'd worry about that is that, or at least one thing that comes to my mind right away, is that the rho is relatively conspicuous in hadron phenomenology, but the A1 isn't. It exists. It's relatively heavy. If you want SU2 times SU2 chiral gauge bosons, the rho isn't enough, so you need the A1, but that's a little worrisome. But worse than that, the pion was also supposed to be a pseudo-Goldstone, an approximate Goldstone boson of the same symmetry. With our modern understanding, that's clearly wrong. You can't make the same symmetry, both a gauge symmetry and a global symmetry that would have Goldstone bosons. So it won't come as a surprise that the pieces didn't fit together. But at some point in the fall of 1967, I think while driving to my office at MIT, it occurred to me that I'd been applying the right idea to the wrong problem. It's not the rho that's massless, it's the photon. Its partner is not the A1, but the massive intermediate bosons, which since the time of Yukawa had been suspected to be the mediators of the weak interactions. Once the ideas were in place, Weinberg writes it was not difficult to make a model. And soon what we now call the Weinberg's law model of electroweak interactions was born. Ricardo showed the Lagrangian in his talk. But Weinberg didn't make much progress in proving renormalizability. And he writes that was partly because he tried to use unitary gauge, which is notoriously difficult to understand, but also he was hampered because of lack of familiarity with path integrals. Weinberg says he was initially skeptical of the work of Hooft and Veltman because of unfamiliarity with path integrals. In fact, in one of the later lectures, he explains that in this period of his career, he viewed path integrals as a throwback to an earlier epoch in which physicists distinguished particles from fields. Whereas, in his view, in today's view, but also in Weinberg's view at this time, the correct picture is that everything are fields. Particles arise from quantization of fields. And path integrals, for example, in the Feynman and Higgs book, he points out, are expressed in particle language, not a field language. And so Weinberg was initially skeptical because of not familiarity with path integrals applied to field theories in particular. And he writes that it was the work of Ben Lee, who derived Hooft's Feynman rules from canonical quantizations, that resolved his skepticism and convinced him that what we now call spontaneously broken gauge symmetry is renormalizable. Assessing the electroweak theory in his Nobel Prize speech, Weinberg says it's all very nice that the original model has passed experimental tests, but he would not have been too disturbed if it had turned out that the correct theory was a different one based on the same ideas. The important thing was a spontaneously broken was an exact but spontaneously broken gauge symmetry. He then goes on in the lecture to talk about the strong interactions in QCD. So experiments increasingly have confirmed QCD as the correct theory of strong interactions. Although the experimental tests, although they were impressive by 1979, when he gave this lecture, of course, are nothing compared to what we have today. But then he highlights one consequence, which also was discussed in some detail by Howard. It's the impact of QCD on our understanding of symmetry principles. The constraints of gauge invariance and renormalizability proved enormously powerful and forced the Lagrangian to be so simple that the strong interactions, as described by QCD, have to conserve a lot of global symmetries that are not exact symmetries of nature. Here's some of them. I guess we should also add strangeness and flavor SU3 and parity. Famously, this doesn't work for CP. Not parity, therefore. Famously doesn't work for P or CP, which led to Steve's proposal of the axion to fix that issue. And that, of course, is a still unresolved question in physics, whether there really is an axion, whether that's the right interpretation of why the strong interactions conserve CP. Concluding the lecture, he writes, I suppose I tend to be optimistic about the future of physics, and nothing makes me more optimistic than the discovery of broken symmetries. So that's Steve at the Nobel Prize acceptance in 1979. Now we're going to jump ahead almost 2 decades to what is quantum field theory and what did we think it is. And as you see, the main change is a rethinking of everything, reformulation in terms of effective field theory as the central tool to organize what we know. So here's Weinberg describing his views early in his career. And it'll be, of course, the views that he described in the Nobel Prize speech. Well, first of all, 2 things especially attracted me to renormalizability in field theory. One was that the requirement of renormalizability is a precise and practical criterion of simplicity. And the other thing, I think this one is interesting, and this one he doesn't really critically discuss later, at least in this lecture, to what extent it held up or doesn't hold up. The other thing I liked about quantum field theory was it gives a clear answer to the ancient question of what it means for a particle to be elementary. It's just a particle whose field appears in the Lagrangian. So with the modern duality understanding, well, one of the limitations of this statement, which Steve really doesn't discuss in the lecture, has to do with dualities. So anyway, Steve explains, as Howard also did, that he changed his viewpoint largely in the course of teaching about quantum field theory at Texas and writing his books. He came to view quantum field theory as the inevitable low energy outcome of relativity plus quantum mechanics plus cluster decomposition. So quantum mechanics means that you're going to have a Hamiltonian, a Hilbert space and a Hamiltonian acting on it. But relativity, well, okay, why is the Hamiltonian built as an integral of local operators? Because there has to be another Hamiltonian in a different Lorentz frame. And if you want to have Hamiltonians in different Lorentz frames, or if you want Hamiltonian quantum mechanics to be relativistic and satisfy cluster decomposition, he claims to show that the Hamiltonian has to be the integral of local operators. So you get the structure of quantum field theory. Why are there Lagrangians? Because otherwise there's no link between symmetries and conservation laws, and Lorentz invariance is difficult to achieve. So he writes, he says, although you can't argue, I think he means you can't argue rigorously that relativity plus quantum mechanics plus cluster decomposition leads only to quantum field theory. He said you can't argue this because he points out string theory as an example of a theory that satisfies relativity, quantum mechanics, and cluster decomposition, but it's presumably not a quantum field theory. So you cannot argue that these principles lead only to quantum field theory, but you can argue it's very likely that at sufficiently long distances, any such theory looks Lorentz invariant and satisfies the cluster. You can argue that any theory that at sufficiently long distances is Lorentz invariant unclustered decomposed will also look like a quantum field theory. So he's saying that you can't argue that these principles lead only to quantum field theory, but that anything that satisfies them will look like a quantum field theory at low energies. I think most physicists today would find this convincing, and certainly I do. Although a quibble is that, a quibble is that his derivation does not apply to theories that aren't infrared free, and so cannot be described in the language of particles. But his statement is also believed to be correct in that case, even though his explanation does not apply to that case. So anyway, this is Steve's explanation of why quantum field theory, that it's the inevitable low energy consequence of more general principles, which he takes to be relativity, quantum mechanics, and cluster decomposition. Cluster decomposition just means that a process here can be described independent of a process in the next galaxy. Well, what's the reason for the gauge invariance of the standard model and general relativity? One possible answer is that it's the only way for massless particles of spin 1 or 2 to have non-trivial couplings at low energies. This is a reference to the work he had done in 64 and 65 on soft theorems and QED and gravity. And in my list of 6 topics at the beginning, it's the only one that the previous 2 lectures didn't really say much about. And I won't either, because I want to go into other things. But I would quibble slightly with this proposed explanation. I would say that this is a true and important fact, that the only way for massless particles of high spin to have non-trivial low energy couplings is to have gauge invariance and general relativity. It's a true and important fact. It's one of the many things that Steve pioneered back around 1964. And his work on these questions was the state of the art until the last few years. But I don't find it convincing as an explanation. To me, it shifts the question to why there are massless particles of spin 1 and 2 that do not decouple at low energies. And I don't think we have better explanations today. I don't think we have a full understanding today. Now, as I've already foretold, in 1997, relative to his earlier view, Weinberg drastically demoted the concept of renormalizability. He no longer saw it as a fundamental principle, but rather as a powerful tool in looking for a useful description of most of the experiments we can actually do, because we're mostly limited to comparatively low energies. In other words, quantum field theory, for instance, to begin with, is not necessarily fundamental. It's the inevitable outcome of more general principles. But a refinement of this statement is that quantum field theory at sufficiently low energies always looks renormalizable. And so that was, by 1997, Weinberg's view of why renormalizable is useful. Most of the experiments we can do are going to be describable by a renormalizable quantum field theory, because first of all, quantum field theory is inevitable at sufficiently low energies, but at energies well below the cutoff, whatever it is, any quantum field theory will look renormalizable. So that's in spirit of Wilsonian view, as Howard also remarked. So Weinberg emphasized that all our theories of today are effective field theories, low energy approximations to something that's potentially much different at short distances. So he writes, the present educated view of the standard model and general relativity is that these are the leading terms in effective field theory. I don't see why anyone today would take seriously Einstein's theory of general relativity if by Einstein's theory is meant the theory with the Lagrangian just given by the usual Einstein-Hilbert term. So the theory should be the Einstein-Hilbert term plus higher order corrections. And actually, at just approximately this time, one also learned that there's a lower order correction, the cosmological constant, that also needs to be added. Likewise, he writes, since we know that without additional fields, there's no way that the renormalizable terms in the standard model could violate baryon conservation or lepton conservation, we now understand in a rational way why baryon and lepton number are as well conserved as they are, without having to assume they're exactly conserved. Unless someone has some a priori reason for exact baryon and lepton conservation that I haven't heard, I'd bet very strong odds that baryon number and lepton number conservation are in fact violated by suppressed non-renormalizable corrections to the standard model. This lecture was published in 1997, so it's pretty close to the time when experiment was making this statement clear in the case of lepton number conservation. It's unfortunately still not clear today for baryon number conservation. So Steve goes on to address the relation of quantum field theory to S-matrix theory. So quantum field theory had difficulty in the late 50s and early 60s. Some physicists had said, well, maybe field theory is wrong and the fundamental principle is just relativistic S-matrix theory. Steve had always viewed it, S-matrix theory, as impractical. So even though he was at Berkeley, the epicenter of S-matrix theory during some of the crucial years, he had never found it appealing. But he says that quantum field theory is S-matrix theory made practical, by which he means the following. So specific quantum field theories like the standard model make detailed predictions. But he writes, the general structure of quantum field theory has no content beyond the general principles that went into S-matrix theory. Because if you allow yourself arbitrary terms in a low energy expansion of an effective field theory, you end up generating in a low energy expansion the most general S-matrix that's consistent with general principles. Interestingly, though, Steve remarks that he considers the emphasis on analyticity in S-matrix theory to have been misguided, since he views analyticity as a consequence of the more basic principles, relativity, quantum mechanics, and cluster decomposition. Weinberg actually proved a theorem with Joaquim Gomes that they describe as proving that order by order in perturbation theory, an arbitrary theory can be renormalized, provided one's willing to include all possible local operators as adjustable counterterms. I think you could describe it by saying that including non-normalizable operators does not lead to any anomalies beyond the known ones that occur for minimally coupled fermions, or at least this assertion is part of the theorem. So, in the concluding part of his talk, Weinberg responds to those who found it discouraging to demote the gauge invariance and other aspects of the standard model from fundamental principles to low energy approximations and an effective field theory. So he's responding to those who find it discouraging to question the fundamental significance of the deepest theories we have. He says, in regarding the standard model and general relativity as effective field theories, we're simply balancing our checkbook, realizing we perhaps didn't know as much as we thought we did. But this is the way the world is, and now we're going to take the next step and find an ultraviolet fixed point, or much more likely, find entirely new physics. So that's the note on which he concludes in 1997. So we'll jump ahead to 2018, near the culmination of Steve's career, where he looks back on half a century of the standard model. So here's Steve's assessment of where physics was when he started. Feynman, Schwinger, Dyson, and Tominaga in the late 40s had figured out how to calculate in QED in a Lorentz invariant way and to deal with the infinities. But more than that, the theorists of the 1940s had discovered a rationale for the simplest version of quantum electrodynamics. The symmetries of electrodynamics, Lorentz and gauge invariance, by themselves would not take you very far. For instance, you could add terms to the Lagrangian that would make the magnetic moment of the electron anything you like. But then renormalization would not work. For the theory to be renormalizable, the Lagrangian had to be very simple. And it was in just that simple theory that you could calculate specific results and get stunning agreement with observation. So for instance, you got a unique answer for the magnetic moment of the electron if you make the theory renormalizable. If you don't, you have a more complicated theory, it's not renormalizable, and there's no predictive power for the magnetic moments. So that's what had attracted Steve to QFT. In the 1950s and much of the 60s, it was hard to make progress with quantum field theory. So some physicists, not Steve, explored S-matrix theory, trying to understand the S-matrix by general principles without field theory. This aim, he writes, was in a sense achieved much later in effective field theories, but it could never be implemented in the way that was tried in the 1950s. Complex analysis with many complex variables is just too hard. When he says the aim was achieved in effective field theories, he means what I said before, and I think we'll repeat it in a different way, that if in an effective field theory you allow in a low energy expansion arbitrary local gauge invariant terms that satisfy any fundamental symmetries you want to impose, then at least in an expansion in the energy, you generate the most general S matrix consistent with all the principles you've imposed. So anyway, this is what attracted Steve to quantum field theory, and this is what didn't attract him to S matrix theory as a substitute for quantum field theory. Now Steve writes, the importance of symmetries was clear, but there was a puzzle. Why were there approximate symmetries? So roughly as he had said in the Nobel Prize speech, he writes, if symmetry principles are fundamental truths about nature, how could they be approximate or apply to some interaction, not others? If they are not fundamental truths, what are they? And as in his Nobel Prize acceptance speech, he went on to tell the story of how the standard model had developed. I won't repeat that part of it. So now we have the standard model, he writes. He says, I guess, since this was originally a lecture. Its success is also the success of quantum field theory. Or is it? Since the 1970s, we've understood that within broad limits, any relativistic quantum field theory will look like a quantum field theory, what's called an effective field theory, at energies E less than some fundamental scale m. As I like to put it, non-renormalizable theories are just as renormalizable theories. This is what he'd proved one version of in the paper with Gomez that I mentioned before. He means by this that an arbitrary theory free of the usual anomalies can be renormalized order by order in perturbation theory, provided one's willing to allow all possible counterterms. But to a certain order in the energy, only finitely many counterterms are important. So you gotta, if m is the cutoff, then to a given order in 1 over m, you can describe all observables in terms of finitely many adjustable parameters. But if you manage to measure to a higher order in 1 over m, you'll encounter more adjustable constants. So to me, this discussion by Weinberg raises a question about which, as far as I know, he never directly expressed an opinion. He's saying that order by order in perturbation theory, you can construct a family of unitary physically sensible S matrices with the coefficients of all possible local operators as free parameters. To me, this raises the question, do unitary S matrices with those parameters actually exist, or is this only a perturbative statement? I actually wonder if Steve, to my knowledge, he never addressed that question. I never heard it, and I didn't see it in any of the papers. I actually wonder if he considered the question irrelevant because of his view that quantum field theory was fundamentally effective field theory. But he didn't explicitly say that he considered it irrelevant either, as far as I can see. So I'm not sure. He also, at times in his career, was very interested in ultraviolet safety, the existence of a UV fixed point, possibly including gravity. And as he would usually say when he discussed ultraviolet safety, that would be a framework that would very likely allow only a finite number of free parameters corresponding to relevant or marginal perturbations. So if ultraviolet safety is correct, that would be a principle that would select a very small family of the infinite dimensional family, and maybe those are the theories that really exist non-perturbatively. Steve had a consistent interest in this idea, which might entail a fundamental quantum field theory that really exists non-perturbatively. But as far as I know, when he generally viewed this as a sort of dark horse, not the most likely prospect. He used to say, and that includes in the lectures I'm describing, that the likeliest future prospect would involve a completely different kind of physics, possibly string theory. But Steve always used to try to be open to all possibilities, including the ones that look less likely. So he would often discuss ultraviolet safety as an option. But anyway, regardless of whether you think ultraviolet safety is the way to go, the question of whether the family of unitary relativistic S matrices, depending on infinitely many parameters, really exists, or only makes sense in perturbation theory, as I said, I'm not aware that Steve ever expressed an opinion. For what it's worth, I think it's an interesting question, and I'm not sure of the answer, but I tend to think the answer is no. If the answer is yes, I don't think it will be because there is a universal fixed point that has all the infinitely many parameters as relevant operators. I think it's more likely that the generic theory has a UV limit of a type unfamiliar to us, not the ordinary local quantum field theory fixed point. So I guess the answer is no, but if it's yes, I think there's something in the ultraviolet that we really don't understand. That's the ultraviolet of a generic theory in this family. So I think that for the same reason Steve said that asymptotic safety would leave only finitely many parameters. Anyway, Steve in 2018 considered any quantum field theory to be as good as a renormalizable one. What's special about quantum renormalizable theories, he explains, and I've said this already, is that any theory looks renormalizable, possibly free, which is a special case of renormalizable. But anyway, any theory looks renormalizable at low energies. Unfortunately, in most observations, only relatively low energies are accessible to us. Famously, the existence of gravity is one probe of high energies. Neutrino masses are probably another, though we don't know for sure. In inflation and cosmology, we probably are getting a window beyond renormalizable energies. And baryon non-conservation might ultimately be another window. There can be a few, but mostly we only are able to probe relatively low energies. And Steve writes that with hindsight, that's why the search for renormalizable theories turned out to be such a good idea. Remember, in the early part of his career, symmetries, including approximate symmetries, and the drive for renormalizability was the driving force. And with hindsight, he's reinterpreting why it was a good idea, but it was a good idea because whatever was the truth of nature at accessible energies, it was likely to be ascribable by a renormalizable theory. Now, as in the previous two lectures I summarized, as well as some others that were described by Howard, Weinberg notes that global symmetries can be low energy accidents resulting from the structure of gauge couplings, and as such are likely to be violated by corrections to the renormalizable part of the standard model. By 2018, he could point to neutrino masses as a likely confirmation of this picture. Unfortunately, only a likely confirmation because there are other conceivable models, interpretations of neutrino masses. And I think I'll leave the last word to Steve. Steve was often finished his lectures on an optimistic note, and here's what he said at the end of this one. The present generation of young physicists may envy those of us who had the excitement and delight of developing the standard model. This might be a mistake, just as it turned out that my generation would have been mistaken to have envied the earlier heroes of quantum electrodynamics. Our newly minted experimentalists and theorists now have a chance to participate in taking the next big step beyond the standard model. They may even be able to see their way clear to the very high energy scale where a final theory will be revealed. Thank you for your attention.
Thank you very much for this very interesting talk. So I think we have time for a few questions. Let's see. Alberto.
Hi, can you hear me?
Yes.
Hi. So I would like to understand better your point about massless spin 1 and spin 2
Yes.
particles. Somehow you're saying there could be particles like that completely decouple at low energy, so somehow they don't have any
It depends.
monopoly interaction. They can only interact with mu, for instance.
Well, it's more clear in the case of spin 1. So in conventional quantum field theory, you could certainly have a U1 gauge field with no charged particles that it couples to. So it would couple only through F mu nu, and therefore it would only have derivative couplings.
That's true. Still, we would need, if we were to write Lagrangian, a local Lagrangian for it, we would need an A mu with the local gauging.
That's true. Although you couldn't deduce it the way Steve approached it. You're right. That's right. Yes. That's a valid point. So at least in Lagrangian field theory, Steve's argument assumed non-decoupling, but you could make another argument if you assume Lagrangian field theory. Steve's argument was sort of S matrix theory plus non-decoupling, and then he tried to deduce properties of Lagrangian field theory. But you're correct, I think, that in Lagrangian field theory, to write a local Lagrangian for the massless spin 1 field, I think requires gauge invariance because it doesn't have enough felicity states to be described otherwise.
Thank you.
But let's go back to what Steve said, though. see, okay, what you said is valid, as I think perhaps possibly as an objection to what I said, but I will stick with what I said as a possible objection to what Steve said. So he proposed that the soft theorem was an explanation of the general covariance in the real world. But it's only an explanation of general covariance if you know about the existence of a massless spin 2 particle, which most people would say is part of what you're trying to explain. Anyway, unfortunately, okay, because there were so many other things to discuss, I didn't explain in much detail Steve's work on the soft theorems in 64 and 65. It was certainly one of his important contributions, and he made important discoveries about that circle of ideas. I'm just quibbling with exactly what you learned about the relations between the different ideas. But there's no question those were important things. I see a question from, well, I see several hands up.
Yes, there are several. Maybe let's see if we, first was Georgie.
Hi, Edward. That was a very nice talk, very insightful. I have a question about the part where you mentioned string theory as a possible sort of new physics that is consistent with effective field theory. Do you see ways of string theory going beyond effective field theory, and could you comment on that? In what way that could happen?
Well, effective field theory is valid at low energies and long distances. So as far as we know, there's no way to get around effective field theory at low energies and long distances. If there was, it would be incredibly important, regardless of whether it came from string theory or someplace else. I mean, I've thought a lot, but fruitlessly, and I'm sure others have, of whether there's any way consistent with general physical principles that you could modify effective field theory at long distances. As far as I know, the answer is no. I'm never going to claim something like that as an absolutely bulletproof statement. Maybe someone will show that, who knows how.
How about examples in string theory of backgrounds where the short distance and the long distance mix, the so-called UVIR mixing? Can you comment on that?
I believe you can always describe it as I believe the mixing description, it's too complicated and technical to remember all the answers, but I believe actually you can't really violate effective field theory in a situation where an effective field theorist would expect it to be valid.
Even in time-dependent backgrounds?
I can make no promises. Time-dependent backgrounds aren't that well understood in string theory. And it's conceivable, it's definitely conceivable there are surprises there. I mentioned that Steve never expressed an opinion on whether the infinite family of theories exists non-perturbatively. And I also said I thought it was an important question, but I didn't quite explain why. In the 1 + 1 dimensional case, if that infinite family of theories really exists non-perturbatively, it would be the natural arena for string field theory. I tend to believe it doesn't, but I don't know that. If it does, the UV is not something standard like a fixed point. It might be something more like the TT bar deformation of Zamochikov.
Okay, thank you.
Maybe we have time for one last question. Alexander.
Myself.
Okay.
Cannot unmute myself. Now, okay, thank you. Yeah, thank you for this very nice reconnection, this talk, very nice. So I have one question. I mean, the argument of deriving QFT at low energies and also string theory, it's cluster decomposition, relativity, and quantum mechanics, as you say. Is there any way of parameterizing what happens if you were to give up the canonical way of standard quantum mechanics, so to speak, in this argument? Is there a way of parameterizing what would come out of this?
You want to give up, you want to modify quantum mechanics?
Yeah, something in some way, in some controlled way, so and then see what comes out at low energies, whether there's something else than these two known consequences.
I have bad news, which is even if you don't have relativity and cluster decomposition, well, I think you might, even if you don't have relativity, there's no known way to modify quantum mechanics, keeping cluster decomposition and being physically sensible. So let me give you an example of that statement. Mm-hmm. So Google did this famous experiment where they had 57 qubits and they did a complicated calculation. And got answers that went beyond what you could check with a classical computer, or at least that's their original claim. And they definitely tested quantum mechanics under conditions of complexity much greater than those where quantum mechanics had ever been tested. But they did not describe their experiment as a test of quantum mechanics, even though it clearly was a very interesting and new test of quantum mechanics under conditions quite different from any previous test. Why did they not say it was a new test of quantum mechanics? They actually did not say why they didn't, so I'm only guessing. But I believe the reason they didn't is that there's nothing to compare quantum mechanics to. Because there's no physically sensible candidate theory that modifies quantum mechanics that you could compare their computation to. Because there isn't any known consistent way to modify quantum mechanics keeping cluster decomposition. Forget relativity, even without relativity.
Okay.
So I believe that's why Google didn't interpret their experiment as a test of quantum mechanics. It's somewhat similar to the reason that the LIGO people tend to not describe their observations as tests of general relativity. They agree with general relativity, but there isn't a convincing, well, it's not clear what's the competing theory you'd want to compare to. So they can't, well, it's artificial. It tends to be artificial to try to put limits on parameters in competing theories. You can do something, but anyway, the LIGO people tend not to do it. I think for the same reason the Google people didn't. Anyway, I think that's the trouble with your question.
Okay.
First, you have to decide how you want to modify quantum mechanics.
No, I agree. The idea would be to modify it, keeping cluster decomposition. If you say that's impossible, then
I don't want to say it's impossible. I'm just going to say that the literature doesn't contain a sensible suggestion, I don't believe.
Okay, okay.
I could be wrong. I definitely don't know everything in the literature.
Is it known which, like, if you take, for instance, quantum mechanics as from Dirac's little book, basically, right? The axioms, if you want, in there, like what there ties most closely, though? I mean, like, from which is part of these axioms cluster decomposition actually kind of follows, or which is it most closely tied to? So that you would know if you don't want to give up cluster decomposition, you are not allowed to modify.
Exact. Well, Weinberg explored some modifications of quantum mechanics, which I didn't review for this lecture, and I better not try to talk about them now. But Joe Polchinski, and I don't remember exactly how this was related to Weinberg's work, but Joe Polchinski showed that in some modifications of quantum mechanics, you could signal superluminally at a distance. So famously, the Einstein-Podolsky-Rosen correlations cannot be used for superluminal signaling. But if you modify quantum mechanics, you're in danger of being able to signal superluminally. The reason I've told you this in answering you is that in Dirac's book, it's, I believe, sufficiently abstract that you wouldn't be able to talk about whether there's superluminal signaling. So you need to input locality or cluster decomposition along with quantum mechanics before you can ask whether the correlations can be used to make signaling at a distance. If you just say abstractly there's Hilbert space and operators, then you can't try. You need more than that to be able to talk about signaling at a distance.
Okay, thank you. Yeah. Okay, so I think it's time to move to the last talk, and then we will have some time after for a general discussion. So the next speaker is Professor Nima Arkhani-Ahmed from the Institute for Advanced Study. Nima.
Can you guys all hear me okay?
Yes, yes.
All right, wonderful. All right, well, it's really an enormous honor to speak at this wonderful occasion here today. The organizers tasked me to talk about two aspects of Steve's incredible body of work on two different aspects on gravity as an effective field theory and the cosmological constant. These are two different topics, but I was, in any case, most delighted with my charge, since these do represent aspects of Weinberg's work, which have had the biggest impact on the arc of my own research over the past 20 years. As we all know, Weinberg loved to ask simple and deep questions, perhaps prime amongst them, why is nature described by quantum field theory? And he was also a great unifier. He famously disliked the Einsteinian view of gravity as curvature of space-time, feeling that it gave gravity too privileged a position relative to the other interactions as giving the arena in which everything takes place, and feeling that this erected an artificial barrier towards seeing a deeper unity between gravity and the other interactions. So this led him to a point of view about gravity as an effective field theory, much like other effective field theories describing massless particles of spin 2 in flat space. And this was more generally part of it, is very deep, and I imagine for the time, highly unusual reimagining of the foundations of, and even the raison d'etre of quantum field theory itself, asserting the primacy of relativity, quantum mechanics, and the notion of particles as a starting point. So that's where we're going to start the story. So if we ask the question, why quantum field theory, of course, the most obvious textbook answer, I imagine, from the middle part of the century would have been because we see classical field theories in nature and we should quantize them. But Weinberg was dissatisfied with this. And he promulgated a point of view, especially in his field theory books, which is that quantum fields offer the most useful formalism to describe fundamentally particles that have local interactions satisfying, as we've discussed already, cluster decomposition and so on. And this has a much stronger feeling of inevitability about it. Whatever the underlying theory of the world is, so long as it has relativity and quantum mechanics at low enough energies, long enough distances, it's guaranteed to be described by a quantum field theory. But it's a notion of particle that is primary here. We're trying to describe consistently the interactions of particles, and local fields are a convenient tool for doing that. So as Weinberg does, and really going back to Wigner, we begin with the very simple question, what is a particle? And most abstractly, a particle is a unitary irrep of the Poincare group. The intuitive idea of a particle, like an electron here being the same as the electron there and in other places, and rotated, the spins rotated in different ways and moving at different velocities, the fact that we give them all the same name, electron, is a reflection of the space-time symmetries. So we have the space-time symmetries that have to be implemented in a unitary way on a Hilbert space because of quantum mechanics. And so you can imagine that a particle, just by diagonalizing translations, is characterized by giving some energy and momentum, satisfying the on-shell mass condition. And it can have some other labels too, sigma. And we can start from some reference momentum and define all other reference momenta by some canonical boost that takes us from K to P. And we can use the unitary representation of that special boost to define what I mean by the other labels that the particle might have other than its momenta. But once you do that, you're stuck. And if you take a general unitary transformation corresponding to a general Lorentz transformation on a general state, you will mix these indices up with each other in general, and they will transform under not the Lorentz group, but the action of the Lorentz group, and is intuitively clear, where corresponds to those Lorentz transformations that leave the momentum of the particle invariant. Okay, and those are what correspond to the additional degrees of freedom, the spin degrees of freedom, which transform not under Lorentz transformations, but under the little group, Wigner's little group of the Lorentz transformations. So so that's what particles are. Now we imagine that we have some particles interaction, some in states of particles, out states of particles. And here is the logic that that leads us to fields. We begin by just trying to label all of the states of various particles. We define raising and lowering operators. This just defines them as ways of simply characterizing operators in this Hilbert space. Now, crucially, we want to build some interaction Hamiltonian so that the scattering processes involving these elementary particles satisfy the very minimal notion of locality that goes into cluster decomposition, which very precisely said that if I look at the connected part of the scattering amplitude for a bunch of particles, there should only be one overall delta function for momentum conservation. I shouldn't have two different pieces of delta function for momentum conservation, which would products of two different pieces that would tell us that what's going on here is not uncorrelated with what's going on arbitrarily far away. And in order to do that, you have to build the interaction Hamiltonian as an integral over something local over space of some Hamiltonian density. And in order for these things to transform nicely under the symmetries, translations, and so on, we should build functions of position. These fields phi plus or minus out of a position that I make from taking linear combinations of the A's and the A daggers. So that's why fields are useful for describing the local interactions of particles. And this much has nothing to do with the Lorentz invariance. Finally, with Lorentz invariance, in order for time evolution in one frame to actually give us the same answer for the S matrix as doing things in any different frame, we have to have the time orderings and the definition of the perturbative expansion of the S matrix don't matter, which forces that the Hamiltonian density should commute with itself outside the light cone, which in turn tells you that the Hamiltonian density has to be built out of those particular combinations of phi plus and phi minus that we normally identify as relativistic quantum fields, giving us a notion of antiparticles, spin statistics, and so on. All right, so that's the sort of rough logic. We're trying to describe the local interactions of particles, and we use fields as the convenient way of doing it. Now, the moment we have particles with spin, life gets a little bit more interesting because the amplitude itself only has little group indices. The amplitude does not transform like a Lorentz tensor. If you do a Lorentz transformation on the momenta, you have to pick up a little group transformation on the little group indices. What we, however, compute with fields are things that are Lorentz tensors. So here's an example of what we do with with the spin 1 fields, for example. So in order to go from one to the other, we also have to have polarization vectors, which are objects that sort of convert between Lorentz and little group indices. And we can think of, again, intuitively as putting the fields that we see on the right-hand side on shell to get the actual amplitudes of the particles on the left-hand side. And this is all well and good, except for the very well-known, but also very important and dramatic difference between massless and massive particles. The degrees of freedom for massless and massive particles, the structure of the little group for massless and massive particles with spin. The massive little group in d space-time dimensions is just d minus 1 dimensional rotations, but the massless little group is d minus 2 dimensional rotations. That's the intuitive fact that a spin 1 particle, for example, a massive W, no matter how it's moving, you can go to a frame where it's at rest and you can tilt your head and see it spin in all 3 different possible ways. And a general spin S particle is 2s plus 1 degrees of freedom, but you can't do that with a massless particle. You can't catch up with it. And so all we can talk about, the only spin degrees of freedom that it has is helicity, the spin in the direction of motion. So really fundamentally only 1 degree of freedom is forced on you for a massless particle with spin. If you have a parity, even in some approximation, it's 2, because you should be able to see it both helicities. So this dramatic difference between the number of degrees of freedom of massless and massive is an extra challenge for the field description. And we can see that very simply in the structure of the polarization vectors. If we start with spin 1, for example, epsilon mu, of course, is 4 degrees of freedom. If I want to describe the 3 degrees of freedom of a massive spin 1, I can do that by imposing epsilon dot p equals 0. That gives me 3 degrees of freedom. That's good. But if I have massless spin 1, I just can't do that. There's simply no Lorentz invariant way of getting down to the 2 degrees of freedom associated with a massless spin 1 particle. And if you make some arbitrary choice for how to label the 2 polarizations for the massless spin 1 particle, if you do a Lorentz transformation that leaves a momentum invariant, you'll see that you won't come back to the same form of the polarization vector, and it'll instead shift by something proportional to the momentum itself. Therefore, if we want to use this strategy of using local quantum fields to describe the interactions of these particles, we have to introduce a new idea. We have to declare a redundancy that helicity states are labeled by equivalence classes of polarization vectors that are shifted proportional to the momentum. This is what the shift looks like for spin 1. This is what it looks like for spin 2. Of course, we can recognize these as linearized gauge transformations or linearized diffeomorphisms. But from this point of view, they're just sort of forced on us simply by trying to describe the correct number of degrees of freedom. Now, this redundancy means that there's a huge constraint on whatever the Feynman amplitudes are for massless particles with spin. If we're supposed to get the same answer, no matter which representative in this equivalence class we choose, then the amplitudes had better be invariant if I shift the polarization vector proportional to their momentum. And so for massless spin 1, we have to have this constraint that p mu dotted into m mu with any other indices is equal to 0. For spin 2, similarly, again, p mu dotted into m mu nu with any other indices should equal 0. From the conventional approach, these are the on-shell word identities. But and in the conventional textbook way of thinking about these come out pretty late in the development. From this point of view, they're primary because they're what's necessary in order to make sure that, despite appearances, the amplitudes are actually physically Lorentz invariant. The mu nus are good Lorentz tensors, but the polarization vectors are not. Only these equivalence classes are Lorentz invariant objects, and so this is what's necessary in order to consistently describe the reduced number of degrees of freedom for massless particles with spin. In Weinberg's hands, this turned into astonishingly restrictive and powerful statements of the Weinberg soft theorems. And the Weinberg soft theorems tell us about all consistent possible long-range forces. So Weinberg started with the idea to imagine you have n particle scattering, but with an n plus with one additional particle, which has a massless particle with some spin s and some momentum q. And the question is, what could the leading amplitude look like as q goes to 0? Now, it's possible for the amplitude to have a singularity as q goes to 0, and the only places it could have a singularity are where where the massless particle is attached to an external line. That's because the sort of propagator here has a 1 over p plus q squared minus m squared, which is just a 1 over p dot q. So we can have singularities coming from when the particles are attached to the external leg. And so what can the leading possible behavior look like? Well, so here I've written down what it could look like for particles of spin 1, 2, potentially particles of massless spin 1, 2, 3, and higher. And so let's say for spin 1, I'm just giving a name to the coupling EI here. And here we make a very important assumption that we put in the leading possible coupling. So we want the largest coupling that we can have, the one that's going to give us a long range, that can conceivably give us a long range force. And therefore we want to have as many powers of the hard particle momenta as we can. So that's why there's a momentum sitting up here. So in all this discussion, we're talking about these leading couplings. And okay, so here's the leading coupling that we can have for spin 1. For spin 2, I can have 2 hard momenta upstairs contracted into an epsilon mu nu. Spin 3, 3 hard momenta contracted to an epsilon mu nu sigma, and so on. So that's what the leading behavior can possibly look like, independent of any other details. But now there's a very big check that we have to do. We have to check invariance under the shift of the polarization vector by something proportional to its momentum, which in practice just means that we contract one of these indices into the corresponding momentum. So we have to have, therefore, that for the massless spin 1 case, that 0 is equal to what we had before, where I take one of the indices of the epsilon and I dot it into p. So in this case, I just get the hard momentum pi dot q over pi dot q. That just gives me the sum of all the charges. So I learned strikingly that just consistency tells me that I have to have charge conservation. Massless spin 2 is the most interesting case. Now, if I have the couplings of the massless spin 2 particle, the various couplings are kappa I. Now, my effective charge has an extra momentum in it. So the charge conservation now, the effective charge is these kappa I times the momentum. So now I have to have that the sum of all these kappa I pi is equal to 0. And that naively seems impossible because I already have a constraint that all the momenta have to add up to 0. If I put a random linear combination of the momenta also having to add up to 0, that puts too many constraints on the kinematics. So the amplitude would have to vanish except for very special possible configurations. And the only way to avoid that is if all the kappas are equal to each other. So that's a remarkable thing, that if you have a massless spin 2 particle, all of its couplings have to be universal. This is the discovery of the principle of equivalence, but only from the consistency of special relativity and quantum mechanics. If we move on to the next case of massless spin 3, now the effective charge is some rho I, but now something quadratic in the momenta. And now it is impossible beyond 1 + 1 dimensions. In 1 + 1 dimensions, of course, something very special happens because the particles are just invert their momenta. The kinematics is so degenerate. But in higher dimensions, it's simply impossible to impose both momentum conservation as well as this quadratic constraint on the momenta, and not force the momenta to only take certain discrete set of possible values. So we learned that we cannot have long-range forces mediated by particles of massless spin 3 and higher. If we do have long-range forces mediated by massless spin 1 particles, they have to have something like charge conservation. Massless spin 2 particles have to have the principle, have to have universal coupling and the principle of equivalence. And you can follow on from this logic by looking at the huge constraint imposed by these on-shell word identities to show that the only way that you can make objects that satisfy those on-shell word identities is to have them come from underlying Lagrangians that have nonlinear, general nonlinear Yang-Mills symmetries, the general nonlinear diffs, all forced on you by simply requiring these linearized gauge symmetries and the linearized diffs associated with the on-shell word identities. Okay, so, all right, so and I should say that, as Edward also mentioned, in recent years, the Weinberg soft theorem, just in 4 dimensions especially, have been interpreted as associated with infinitely many symmetries on the in thinking about amplitude that's associated with points on the celestial sphere, the 2-dimensional surface that any observer would see on the sort of night sky, looking around. Now, that's a sort of a review of Weinberg's way of thinking about these things, but I can't resist saying a little bit. I'll just flash through this quickly just to give an impression, because it's directly inspired by the sort of Weinbergian way of thinking. But I want to tell you something about the sort of modern on-shell way of understanding these things, directly thinking about on-shell amplitudes. And this entire program is really directly inspired by Weinberg to focus on on-shell amplitudes, crucially with the correct little group transformation properties. But there's a very fateful early departure, which is to not transition to thinking about local quantum fields. So you don't talk about local quantum fields. You don't ever see a polarization vector. You don't ever see these gauge redundancies. The space-time symmetries are made manifest at the outset. The correct little group transformation properties in particular are made manifest at the outset. But of course, the price in this program is that you have to manually check that the objects that you're writing down are consistent with locality and unitarity. And I just want to at least give the sort of logical structure of how this way of thinking works. To begin with, you introduce a set of variables that manifest the action of the symmetries as transparently as possible. For example, in 4 dimensions, we can go from a 4 vector to the 2x2 matrix by dotting into Pauli matrices in the usual way. And if the particle is massless, this 2x2 matrix is vanishing determinant, so it's rank 1. So we can write P alpha alpha dot as an outer product of 2 2-dimensional vectors, lambda alpha and lambda tilde alpha dot. Often this is sort of just presented as a kind of a cool trick for introducing these spinor helicity variables, but it's not a trick. The point is that it's these objects that transform properly under the Lorentz and little group, because there's an obvious invariance here under rescaling lambda and lambda tilde by opposite factors, which leaves the momentum invariance. And this is precisely the action of the little group. So that if you give me an object, if I have a particle of helicity h, it means that if you give me an amplitude, if you give me a function of lambda and lambda tilde, it has to have a particular scaling if you rescale lambda and lambda tilde oppositely, given by its helicity. And that's it. Once you do that, you have something that manifestly has the correct little group and Lorentz transformation properties, with no need for redundancy in polarization vectors. Okay, so that's the conceptually important thing about the spinor helicity variables. And then you can go on from there. I won't go through this in detail. Maybe the most 2 important things to say is that first, the kinematics of 3-particle scattering is so constrained that you can completely determine the 3-particle amplitudes up to the overall strength of the interaction just by symmetries. Okay, so 3-particle amplitudes are entirely determined by asymmetries. This lets you discover various fascinating things. For example, the leading 3-particle amplitude, for let's say you have all particles with spin curly s, the leading three particle amplitudes have two of them with minus helicity and one of them with plus helicity, or the other way around. There's a subleading one where all of them have a negative helicity, or all of them have positive helicity. Those in a conventional language would correspond to higher dimension operators, but the leading ones that that we would associate with the two derivative theories from the conventional language are ones with minus, minus, plus, and the other way around. And so there are these extremely simple expressions that, amongst other things, for example, tells you that the three particle amplitude for gravity is the square of the three particle amplitude for Yang-Mills. This is a totally unobvious fact from staring at the Lagrangians for GR or Yang-Mills. And there's another amusing feature that these three particle amplitudes appear to have sort of poles in them. If the spin is bigger than zero, they have these kind of objects downstairs. That's important because now the three particle amplitudes are completely determined by symmetries, but now there's a consistency check for four particle scattering, which is that the four particles amplitudes, any ansatz you have for the four particle amplitudes, it has to have poles in a particular spot. In sum of two momenta can go on shell, interpreted as producing the on-shell intermediate particle. And in the neighborhood of that pole, the residue on that pole has to be interpreted as the amplitude for producing the intermediate state from the initial state that then goes out to the final state and produces the friend on the other side. So this is a very simple mathematical requirement on the four particle amplitude. Easiest to implement if we imagine we have a weak coupling, so we're working at something at tree level. And so, but we see very directly the physics of locality that tells us where the poles are, unitarity that tells us that the four particle amplitude has to factorize on the poles in a consistent way. And now, because the three particle amplitudes are completely determined by symmetries up to the coupling constants from before, this is just a well-posed mathematical problem. So for instance, if you compute you imagine you have particles of all particles of spin S, and I just compute what the residue would be in the S channel by just taking the product of these three particle amplitudes up to some overall factors that just take care of the correct weights. You see this interesting feature that it looks like 1 over t to the power of the spin of the particle. So it's not obvious that this could make sense. If we have spin 0, then this factor isn't there. All these residues are just equal to g squared. And so there's trivial to build a four particle amplitude that has the correct factorization property. You just multiply this residue by 1 over s plus 1 over t plus 1 over u. But it's not obviously that it's consistent if you go to higher spin. So for instance, if I take a single particle of spin 1, then by the structure of this residue, the most general four particle amplitude that I could have can look like this. And I can demand that I match the residues in the S and the T and the U channel, and that just puts these simple restrictions on these coefficients A, B, and C. All these differences have to equal 1, and that's clearly inconsistent because if I add all the left-hand sides up, I get 0 equals 3. Okay, so that's not possible. What I can do is have many massless spin 1 particles, and I have the same structure here, but if there is a number of them, A, B, and C, I'm just going to call the strength of this interaction FABC. And now exactly the same conditions turn into these ones. And now these three equations can have a consistent set of solutions, only if when I add them all up on the left, I get 0. On the right, I'm forced that these F's have to satisfy the Jacobi identity. So that's how I discover that I can't have a single massless interacting particle of spin 1, but I can have many of them consistently interacting, but only if their interaction is has the Yang-Mills structure. If we go on to a single massless spin 2, now the same argument gives me a 1 over t squared for the residue. And naively, this is very bad because remember, the amplitudes can only have simple poles in S, T, and U. But remember that this is the residue at S equals 0. So t squared when S equals 0 is also equal to negative t times U. And so I could write the amplitude as with a minus sign, minus g Newton numerator that just takes care of all the helicity weights divided by ST and U. And now, of course, remarkably, beautifully, clearly by symmetry, that's going to have the correct residues in all the other channels. So we discover it is possible to have a massless self-interacting spin 2 particle. But you also discover you can't have more than one of them. You can only have one of them, or if you have more than one, they have to be mutually non-interacting. And if we go on to higher spins in this way, T cubed and so on, there's clearly no way of rescuing that. There's no way of interpreting that as a simple pole in any way. So that's just giving you a flavor of the kind of argument, but it turns into a completely well-posed mathematical problem to just work out the consistent possible couplings of the 3 particle amplitudes. And you can really very directly from this simple 4 particle consistency check deduce this fact that relativity and quantum mechanics tells you that if you have massless particles with spin, then their leading interactions are only consistent for theories of spin 0, 1/2, 1, 3/2, and 2. And that if you do have the massless spin 2 with the leading interactions, and it's unique, and it has to be described by GR, you can have up to 8 of the massless spin 3/2 guys, and that's a structure of supergravity. You can have the massless spin 1 guys that's forced to have the Yang-Mills structure. And all these things are simply forced on you by the consistency of relativity and quantum mechanics. So this is very much in the vein of the Weinbergian sort of inevitability, and is the more modern way of talking about the same things from a very similar starting point, but making a larger departure from the standard formalism very early on by just simply refusing to talk about local quantum fields. Let me just make a couple of other comments about gravity as an effective theory. Of course, gravity is famously non-normalizable, but that's one of the points of view about effective field theories that we can sensibly talk about it in the energy expansion. And as Howard emphasized, that means that even in a non-normalizable theory, the non-analytic quantum logarithms are calculable. So we can talk, for instance, about a graviton loop correction to a 2-point function that might look like just by units g Newton times p to the 4th with some constant a plus b log p squared plus ... The a piece, which is not, the a piece is totally unknown UV physics, but the part proportional to the logarithm, the b is completely calculable in the low energy theory. And the position space avatar of this is that if we look at the shift in, for example, the potential that we would get from such a correction, the piece proportional to A would just give me a contact term, just a delta cubed of R, while the piece proportional to B would still be tiny, but it would be a power law. It would go like L Planck squared over R cubed. It's a tiny but calculable long distance effect. Similarly, I can, for example, talk about photon-photon scattering mediated with gravitons in the middle. And this is a totally calculable quantum gravity computation. Okay? All these pieces with logs are calculable. Exactly what I mean by this cutoff, those pieces are not calculable, and those would add up to one of these contact terms that I can't calculate. It's coming from a higher dimension operator in the standard effective field theory language, but all the coefficients of the logs are calculable. So these are examples of calculable quantum gravity corrections. Of course, gravity is special. So having said all this, gravity is special. There are many ways in which gravity is special. There are some very important qualitative ones. For example, we know that if we talk about extremely high energy scattering in gravity, we eventually make black holes. And when the energies get parametrically larger than m Planck, the center of mass energy gets parametrically larger than m Planck, the black holes that we make grow in size. They get bigger and bigger. Similarly, there are entropy bounds that tell us that the maximum entropy in a region of space scales like the area in Planck units versus what we'd expect from a local quantum field theory, which is a volume in the units of some ultraviolet color. Other structural things, there are no precise local observables in a theory that has quantum mechanics and gravity. A very precise notion of how different gravity is that while we can imagine all sorts of other effective field theories are actually the low energy limit of some underlying quantum field theory, a graviton in d dimensions cannot be a composite particle from some kind of local quantum field theory dynamics in d dimensions. This is the Weinberg-Witten theorem. And actually, we saw an on-show avatar of this a moment ago when I said that you can't have multiple massless spin 2 particles interacting with each other. If you could have some underlying 4-dimensional theory that produces a massless spin 2 particle at low energies, then you could also weakly couple that underlying theory to gravity, and that would give you a theory of multiple interacting massless spin 2 particles, which we know we're not allowed to have. Okay, so all these things make gravity special, and like all great no-go theorems, the Weinberg-Witten theorem has a very famous and important counterexample, which is that we've discovered that the graviton in d+1 dimensions can be a composite particle from local quantum field theory dynamics in d dimensions in the gauge gravity duality between field theory in d dimensions and theory of gravity or strings, etc., in anti-de Sitter space in one higher dimension. All right, so let me now, for the last 10 minutes of my talk, turn to the issue of the cosmological constant. As we all know, and as Weinberg well appreciated, the cosmological constant is a sort of a crushing weight on the notions of naturalness that have that drove a lot of thinking in particle physics for many decades. And one of the first things that Weinberg did in this business is to actually show how much of a crushing weight it was by giving some very simple no-go arguments for why there can't be easy dynamical adjustment mechanisms to explain the smallness of the cosmological constant. So, for example, you might look for some theory that has gravity and a bunch of other fields. You're looking for a vacuum solution, so you're looking for a flat space vacuum solution. So you're looking for a solution where the G mu nu is a constant in space, the other fields are a constant in space. And could it be that if I take the trace of the equation of motion for gravity, which would give me the cosmological constant, that there's some reason why that's actually a linear combination of the equations of motion for the other fields. See, if that was possible, then putting the matter fields on shell would force the cosmological constant to equal 0. And there are many examples that people have tried of building sort of dynamical adjustment mechanisms of this sort. And Weinberg disposed of them all in one shot with the following very simple argument that if such a thing was possible, then it's equivalent to the Lagrangian, at least on the configurations where all the fields are space-time constant, having the following symmetry that you can think of as a scale invariance. If you take all of these fields, you can just divide them up into the ones that are charged into the symmetry and the ones that are not. The one that's charged into the symmetry is some scalar phi, and the symmetry tells you that G mu nu and phi have to come together in this combination G mu nu e to the 2 phi. So phi really looks like a dilaton, and then the Lagrangian evaluated on the constant field can just be this root G hat times some constant V naught, but that gives you a potential for this scalar phi. And so either V naught is equal to 0, in which case you haven't done anything, you're still fine-tuning the cosmological constant, or you have a runaway potential for the dilaton phi that either drags all the mass scales to 0 or to infinity. In any case, that's a no-go theorem for simple adjustment mechanisms for the cosmological constant. Weinberg didn't explicitly talk about this, but you can also ask whether it's, there are ways to get rid of just the vacuum energy part of the energy momentum tensor, and it's also easy to see that you can't do something like that in a simple way, and that's because if I take any homogeneous energy momentum tensor, there's a part of it I can't uniquely decompose it into matter part, radiation part, and cosmological constant part locally. But we know that the matter and the radiation part have to gravitate normally. We're trying to sort of get rid of this part and say that it behaves differently, but there's no local way of deciding which part is cosmological constant and which part is everyone else. You need a causality. You need to, what's special about the cosmological constant is it's the part of the energy momentum that survives deep into the future. And so there's no local mechanism of this sort either that can degravitate the vacuum energy. Of course, famously, Weinberg gave us a totally different sort of explanation for the smallness of the cosmological constant. And in Weinberg's anthropic argument, you imagine what the universe would look like if we did nothing, kept everything fixed, but we made the cosmological constant more natural, by making it more natural, by making it a lot more positive or a lot more negative. And Weinberg's striking observation in 87 was that if you made the cosmological constant just a little bigger, between 10 to 100 times bigger than what it was eventually found to be, back then the bound, today what was eventually found to be, then the universe, if I make it bigger and positive, it accelerates so much that the accelerated expansion rips apart galaxies before they have a chance to form. Similarly, if the cosmological constant was too negative, then the universe would recollapse and crunch before galaxies can form. And so if you imagine that all possible values of the cosmological constant are somehow sampled in some way, then it's not surprising that we should find ourselves in the places of the universe that's either empty or dead. And this argument, Weinberg phrased it as a way of ruling out anthropic reasoning, but it did correctly predict the non-zero value of the cosmological constant, not far from where it was eventually found. I want to say that this argument actually tells us more. First, it predicts, in addition to just the size of the cosmological constant, it sort of makes a parametric prediction that that you could imagine verifying at any point in the history of the universe, that if you look at how the matter, radiation, and cosmological constants scale with time, there should be an epoch where these three lines meet each other. Okay, and furthermore, and that's because in order for structure to form, first matter has to dominate over radiation, and then the cosmological constant should not be bigger than that scale in order to allow galaxies to form. So roughly, all three things, there should be an epoch where all three things happen at the same time. And actually, in slightly more detail, because we have small density perturbations, in order for galaxies to form, we have to have some time for the structure to grow. So there has to actually be a little gap between when the clumping starts and when the cosmological constant finally takes over. So this is the parametric prediction for the scale associated with the cosmological constant, to be given by the temperature at matter radiation inequality, further scaled by this factor of delta rho over rho, the density perturbations of the 3/4. This logic also can, if you imagine that we have dark matter and dark matter WIMPs, it also explains another interesting numerological sort of coincidence that many people have remarked on, which is this, which is the mystery of the equidistant scales. That the weak scale appears to be the geometric mean of the scale associated with the cosmological constant and the Planck scale, the reason for this is that if we have dark matter as a thermal relic, by the usual Friesel calculation, again, going back to Weinberg, we can estimate what the temperature at matter radiation equality is given simply by 1 over the annihilation cross-section for dark matter in Planck units. And so that's something like m dark matter squared over some alpha squared associated with the annihilation, some weak coupling factors alpha squared and Planck. So Weinberg tells us that we have to have the scale of the cosmological constant set by matter radiation. Matter radiation is given by this formula, so it's roughly m dark matter squared over m Planck. And if we imagine that dark matter is given by WIMPs, particles actually near the weak scale, then we would get, we would understand why the scale of the cosmological constant is related to the weak scale and the Planck scale in this geometric mean way. Now, there is some theoretical support to this picture, which, of course, famously people polemically debated a great deal in the early 2000s. One is that string theory is a prime example of what a unique underlying theory could look like, but which has an enormous landscape of, let's call it 10 to the thousands of metastable non-supersymmetric vacuum. And just to sort of push the point and decouple it from the complications of string theory, there's a toy model for what's going on. Imagine the Lagrangian in the world is unique, but really unique, but it's the standard model plus n scalar fields and n decoupled scalar fields. Each one of them has a potential that looks like this, but all the potentials are a little bit different. So the Lagrangian is unique. We have, let's say, 1,000 scalars. It's not so many. We already have 100 degrees of freedom in the standard model. But the point is that even though the Lagrangian is unique, we'll have 2 to the n different possible values of the energy, depending on which minimum the scalar finds itself in for each one of these different guys. And so simply statistically, there's going to be one of them within 2 to the minus n, the ultraviolet scale of the theory of the origin. Okay, so that's an example of how we can get, even with a unique theory, a huge number of different, an exponentially large number of different possible metastable vacua, enough to sort of finally scan all the many different possible values of the cosmological constant. And the second piece of theoretical support is from cosmology that eternal inflation gives a plausible mechanism for populating the landscape. Now, of course, it's suspicious that we would be invoking the presence of all these vacua out there beyond our cosmological horizon in order to explain something about what we see inside our cosmological horizon, and especially ironic that to try to explain the tiny size of our observed vacuum energy, we would be talking about things that are outside our cosmological horizon that are literally made impossible to see by that very acceleration whose tininess we're trying to explain by invoking them. But so that's suspicious, but on the other hand, it could be like that we're on the inside of a black hole. After all, being inside this accelerating universe is a little bit like being on the inside of a black hole. And so could it be the things that we naively think are there outside the black hole are encoded in some scrambled way in physics that we can in principle access inside? So that's something like that is expected to be the case to resolve the black hole information paradox. So maybe there's maybe something like that would make sense in cosmology as well. Let's just say that it's not obvious either way whether this is garbage or not to talk about all these vacua outside in order to try to explain something inside. I also want to stress, though, that there's an aspect of this physics that is not metaphysics. If we go back to this toy example of n scalars, imagine that was the actual model. Those scalars can in principle be seen by experiments in our universe. So you could, in principle, with a high enough energy accelerator, make all these scalars, confirm that the potential looks like this. You could even build bubbles of the other vacua, small bubbles of the other vacua, in principle, verify the couplings vary by shooting things into these bubbles and seeing them come out. So this part is not metaphysics. It's in principle possible from measurements in one universe to conclude that your theory is such that it gives you an exponentially large number of metastable vacua. And if we saw something like that, it would clearly change our thinking about naturalness problems. The part that we don't know how to make sense of is the sense in which these states are or aren't out there somewhere beyond our cosmological rules. All right, now, but we're unlikely to do this anytime soon. Obviously, have big enough accelerators that could see all of these different to produce all these other states and make these bubbles of the other vacuum and so on. So I think that what we can do is think if this way of thinking could impact any other aspect of our thoughts about high energy physics. And there's the obvious question going back and the obvious suggestion going back to very nice arguments of Donahue and others. Could there be anthropic explanations for the Higgs mass? And there's a very natural one that if we again leave everything the same and we make the Higgs mass squared more natural by making it more negative, let's say, then if the Higgs Vev just gets 3 times bigger than the observed value, then we don't have atoms, a plural anymore, because the neutron-proton binding energy, the down quark gets so much heavier than the up quark that the mass splitting between the neutron and the proton exceeds nuclear binding energies. And so we don't have anything other than hydrogen. Okay, so if we make the Higgs Vev much bigger, just by a factor of 3, the long distance world changes in a dramatic way. We don't have all this interesting chemistry. That's an accident of where the Higgs is. This is not remotely as compelling as Weinberg's argument, but it's still rather striking. In the opposite direction, if you make the Higgs mass squared more positive, then QCD breaks electroweak symmetry, and you can show that that all baryons are wiped out by scaleron processes in a world like that. So there is something interesting that if we take the standard model and we imagine making the 2 parameters that are fine-tuned, if we make the cosmological constant a little bigger and the Higgs mass squared a little bigger, it's striking that the world changes dramatically, that it's either empty in the cosmological constant side or no atoms on the Higgs mass squared side. And this is striking. It didn't have to be. And it's a true fact. It's a true fact that would just be a curious fact in the unique vacuum worldview. But you could take it as evidence that somehow the existence of a landscape could actually impact not just our understanding of the cosmological constant, but also of the hierarchy problem and the origin of the Higgs mass. And this is, after all, the sort of central tension of beyond the standard model physics has been between arguments that say that naturalness for the Higgs is correct. We have the picture of supersymmetry, the beautiful unification of coupling constants, dark matter that just fall in our laps on the one side, versus indications for unnaturalness on the other side, that there's no such argument for the cosmological constant. From the very beginning, we didn't have evidence for plate-between neutral currents, electric dipole moments, and so on that should have been there if we had natural solutions to the hierarchy problem. And then, of course, over the past decade, where the hell is everybody? Where are all the particles that are supposed to be there in the usual natural worldview associated with the Higgs? And for me, Weinberg's argument extended to possibly thinking about an anthropic origin of the Higgs, made it possible to entertain this possibility, which is at least my own picture. Someone woke me up in the middle of the night, put a gun to my head and said, what I think is going on. I think what's going on is some version of minimal split SUSY, which is a very particular realization of supersymmetry, which is very unusual from the standard point of view, where the scalars are a parametric loop factor 100 or 1,000 times heavier than the fermions. In this picture, we still retain the successes of supersymmetric unification, dark matter. We get rid of all the phenomenological problems associated with the Flavor-Chain neutral currents and so on. The bottom of the spectrum should be near the TeV scale to be dark matter, but that could mean, in the simplest picture for dark matter, something between 1 to 3 TeV, which would be very easy to miss at the LHC, but would be accessible to 100 TeV collider. This picture did correctly predict that the Higgs mass should lie in this range between 120 GeV and 135 GeV. It's a very mild prediction, but at least it wasn't wrong. And what I want to stress, though, is that this is a picture of the world which we could imagine getting evidence for from experiments, which would be completely crazy without the landscape, but would be quite plausible with it. All right, so that's all I wanted to say. I just wanted to end by saying that I was going to put that Weinberg was my hero and ideal in theoretical physics, but he really continues to be my hero and ideal in theoretical physics. And he somehow struck the perfect balance, as Ricardo also said in the very first talk, between direct contact with experiment and phenomenology on the one hand, but strong tide of formalism, but not just formalism for doodling around sake, but formalism with a deep physical point on the other. And he managed to combine this style to be right about the real world, the actual world when we see outside our window over and over again. And I hope, and I'm sure that his example will serve as an inspiration for us for decades to come. Thank you.
Thank you very much, Nima. And maybe at this point we can move to the discussion session, and we can first start with questions for Nima and then for everybody else.
Oh gosh, I went over even. Sorry, sorry about that.
No, it's okay. It's okay. I mean, we are almost on time, so it's good. So let's see. There are maybe questions in the chat as well, but let's start with the one here. The first is Anupam.
First of all, thanks to all the speakers, and including Nima and also Witten. So I have a question for, I think, both of them in some sense, because they're related. So as we envisaged our quantum field theory, the energy that we have seen, or whatever we have seen from in the sky to the LHC, essentially local quantum field theory works extremely, extremely well. But what happens if I open up this door of non-locality, non-local aspects of quantum field theory, or maybe not, it's not even a quantum field theory, in the UV and in the extreme IR? And this is the part which we have never seen. And what would go wrong, or what would perhaps we will gain if we give up the concept of locality? So maybe Nima can answer, and then maybe Ed can also answer later.
Maybe I can say something quickly, which is that that it is impossible to make just abstract statements, right? You have to like take particular examples and see how they work. But what I can say, what's the problem? Saying the word non-locality is not as easy as you think. For example, you can do things like adding terms to a Lagrangian looks like 1 over box. Say, aha, I've done something non-local there. But things like that are relatively dumb because they're secretly having integrated out something which is a normal locally coupled massless particle. Okay, so first, there can be things that look like they might be non-local, but were actually local. You just integrated something out light that you shouldn't have. Beyond that, I would say, but if you do random things that are non-local, the problem is that in a Lorentz invariant theory, non-local, in a Euclidean theory, non-local means, stretching out over some distance, right? But in a theory with space and time, non-locality has no reason to restrict itself to only be backwards in time. Okay, so you also run into difficulties with acausality if you try to do things that are non-local in a random way. But there are examples, and actually Edward referred to one of them, and maybe I'll leave it to him to say more about it. Instead of just sort of randomly saying things aren't local, you have to find interesting examples of things that seem to slightly violate the rules, the standard rules. So there are these standard rules that we think encode causality and locality in amplitudes. And there are examples of theories, at least in 1+1 dimensions, that violate those rules a little bit. These are associated with these TT bar deformations and so on. So these are some examples of theories that don't quite look like normal local quantum field theories exactly in the usual way in the ultraviolet, but don't badly violate the rules that go into building the S matrix. Whether or not theories like that make sense in more than 1+1 dimensions, 1+1 dimensions is so special that I find it very hard to take any general lessons about life from 1+1 dimensions. I think you can use examples from 1+1 dimensions to illustrate any polemical point you want to make about physics. So I'm very uninterested in theories in 1+1 dimensions personally, but in higher dimensions, if one could find examples like that, that would be fascinating.
Remember Weinberg's points in the last 2 lectures I summarized was that any relativistic Lorentz invariant and physically sensible, by which his cluster decomposition was his way to say physically sensible theory, looks like a local quantum field theory at low energies. And although it's not a true theorem, as Weinberg always emphasized, I believe it's true.
Yeah.
Any departure from that, any way to make a physically sensible quantum mechanical Lorentz invariant theory that doesn't look like a local quantum field theory at long distances would be extremely important. Assuming that Weinberg's folk theorem is true, I'll interpret your question as being, what can we do microscopically? And I'll only say, as Nima said, that it's very hard to do anything sensible. Both the TT bar deformation and string theory are examples that probably are something in that category, but I think the only thing I'll add is that you have to replace locality with something.
Right.
You can't just throw it away.
I should say that this is a historical point. It has never happened to us in physics that progress has happened by taking the previous rules and just saying, aha, look how brave I am, I'm crossing one of them out. Always we learn things that are more rigid than they were before. They never get less rigid. We never lose principles. We sort of gain them. They get more rigid, more constrained. So even, for example, when we say that string theory is somehow deforms away from field theory at high energy, the high energy behavior amplitudes in string theory is softer, it's different than what we can get in local quantum field theory. It actually saturates what you're allowed to do compatible with the principles of analyticity and so on. So in fact, local quantum field theory was a little too lazy. It could have done something like sharper and better. And string theory does that sharper and better thing when it comes to satisfying the sort of principles of analyticity and causality and so on. So it isn't like you find something which is like, aha, out of left field, you just cross out something and start over. It has never happened that way in 4 centuries. I've seen no reason to expect it's going to start happening that way now.
Then there's a question by Chester.
Yes, hello. And thank you everybody for the very fun talks. Nima, I have a question about this general approach to treating the scattering amplitude as the fundamental object. It seems that you're enforcing it being unitary a priori. So are you able to formulate it as an effective field theory descending from a UV complete one?
A very important point that I didn't say, that Weinberg emphasized is that when we talk about effective field theories, you sometimes get the idea that, well, okay, maybe everything is up to some little corrections of order energy squared over cutoff squared and so on. Not unitarity. Unitarity is dead, perfect, sharp at all scales. There are many ways of seeing it, but essentially the only way to get imaginary parts of amplitudes is to put internal particles on shell. So if you have too low energies to produce the new particles, then the effects of the heavy particles do not show up in like slightly deforming unitarity. Unitarity is a rigorous property of the low energy effective theory. Unless, of course, you have enough energy to produce some stable massive particle. If there's some stable massive particle in the deep UV, then you'll miss that when the energies are big enough to produce them. But let's say all the particles in the UV are unstable, then the low energy theory would be rigorously unitary. So this S matrix, you don't need to worry about like little corrections to unitarity if you're trying to describe low energy amplitude.
But does the amplitude approach? Does the amplitude approach maintain unitarity at all energy scales, or is there a cutoff for the EFT?
No, but that's what I was trying to tell you, is that it says that in the amplitude approach, the unitarity is an input, rigorous unitarity is an input, and so it is in effective field theory. In effective field theory, we don't have little violations of unitarity at low energies that grow with energy or anything like that. It's 100% unitary.
Okay.
Enrico, maybe we should also ask for questions also to the other speakers. I mean, to all speak also the.
Oh yeah, sure. Of course, yes.
Maybe the next one, Martin Bauer.
Yes, hi, and thanks for a great series of talks. My question is to all speakers, but also mainly to Nima, because he mentioned it in his talk, and I wanted to follow up on this. It's this argument that you made between the correspondence of scattering amplitude for three-body scattering amplitude for gravitons and the Young-Mills squared that you can make, right? I want to ask whether there's some deeper physics behind this or whether it's just an accident. Because if you just on paper, that looks like it would also violate the Weinberg-Witten theorem if you could write down a theory of gravity as a composite. Like the,
So notice that this is most certainly not saying that the this is not saying that you can think of a graviton as two gluons on top of each other. You kind of can for the 3-point scattering, because if you think about 3-point scattering in Lorentzian signature, I mean, I didn't explain it in detail, but if you think about 3-point scattering in Lorentzian signature, everything is just collinear for massless particles. So you can just split in two. So in that way, the kind of obvious dumbest problem that you can't think of as a graviton is two gluons on top of each other, because when they scatter, they're going off in random directions, so they're not going together anymore, right? You can't think of that doesn't hold for 3 points because they're just going back and forth. But yes, but there is this correspondence between gravity and sort of gauge theory squared. Really, I think that the first place that it was vividly seen was in string theory, where you could understand closed strings, amplitudes for closed strings in a very precise sense as taking a product of amplitudes for open strings. This relation between sort of closed string and open string squared is a very deep thing in string theory. There's many aspects of it that are seen all over the place, but you can also abstract some of it away just for field theory amplitudes in this whole sort of program of Bern, Carrasco, and Johansson on the sort of color kinematics connection, and anyway, ways of double copying field theory amplitudes to turn into gravity amplitudes and so on. So it's not a coincidence. There is something to it. It seems like the deepest origin is the relation between a closed string being two copies of an open string glued together.
And why wouldn't it violate Weinberg written then?
Because it's not, in no sense we're not saying that the graviton is the bound state of two gluons on top of each other. And also the beyond the 3-point scattering, it's not just the product of the amplitudes. You do the product of the amplitudes and there's something else. So there's a relation between them, very simple relation between them, but it's not like literally one is a square of the other. So you're not imagining that the graviton is a sort of composite of two gluons, which would be insane because that these are weakly coupled particles. So I can't have them. As I said, if you even said that it's a composite of two of them, the second two of the gluons scattered, you're dead in the final state, right? Because they're no longer moving together. Nothing is binding them together. So it clearly doesn't work. But the relation is not just this direct product relation at higher points. On the other hand, it is some indication of a very fascinating structural relationship between gravity and Yang-Mills that's very difficult to see by staring at the Yang-Mills Lagrangian and the gravity Lagrangian. If you stare at those things, you would never suspect such a relationship. Even at 3 points, it's not remotely obvious from the gravity Lagrangian that the amplitude for 3 gravitons is the square of the amplitude for 3 gluons.
Thank you.
Okay, then the next one is Glennis, I think.
You have to unmute me. Oh, now I'm unmuted. First, I want to thank the speakers. They were all such wonderful talks, and it's mind-boggling to try to put one's head around what Steve accomplished. And as many of you all said, any fraction of those accomplishments would still be stupendous. I wanted to just add more personally, I think, and these were things certainly the speakers alluded to, but I think it's really important to keep in mind also what kind of a person he was. In my life in physics, I so often, as we all have, I'm sure, encountered people who, rather than really grappling with some question, or would say, oh, it's obvious, or no, we know that's not possible. And Steve was so wonderful about both personally not putting people down, which lots of places people do that when they don't know. He wasn't afraid to say, oh, I don't know, this is worth thinking about, or kindly explain why what the answer to your question was without saying you're stupid not to know this thing. And that was in the olden days, that quality was even more rare, I would say. And then the last thing I just wanted to comment, I mean, besides also the fact that he was so willing to entertain that the common wisdom wasn't really necessarily the correct view. But the last thing I think also, I mean, it's too big an example for me at least to follow, but maybe others could. I mean, his work in the public sphere of writing about, I mean, if you haven't read his New York Review of Books articles, they're so wonderful. Well, like I say, to even minusculely try to aspire to be more like him is probably too much to imagine. But anyway, I just wanted to call people's attention who may not be that aware of his public writing and his wonderful books. Like The First 3 Minutes is still a phenomenal resource that I give to people. Anyway, we were so lucky to have all lived in the period where he was contributing to physics. Thank you all again for your wonderful talks.
I completely agree. I think Dreams of the Final Theory and together with Feynman's The Character of Physical Law are by far the best popular books on physics ever written.
So maybe Enrico. So the next question is from Soldata Bhattacharya. So let me. You're unmuted.
Yeah, yeah. Am I audible?
Yes, please.
Yes, yes.
Yeah. So this is the question for Ed. I just wanted to know what he meant by saying that if you throw enough computer power, you can compute proton scattering.
The question I was asked was,
using.
The question was, with unlimited computer power, could a classical computer calculate proton-proton scattering? The answer to that is very clear, yes. Because with unlimited computer power, this is extremely unrealistic. The stress is on the word unlimited. With unlimited computer power, you could do Hamiltonian lattice gauge theory in real time and calculate any real-time process. Now, no one has even tried to estimate the computing power required because it would be unreasonable. In the real world, to actually do this is what you would probably need is a general purpose quantum computer. But if you ask, is proton-proton scattering accessible in QCD to a classical computer with unlimited computing power? The answer is certainly yes.
Okay, so thanks. If some data is satisfied. So I would again ask for questions also for the first two speakers. If there is anybody. But in the meantime, I do have a question maybe for the first three speakers or maybe all of them. So I think in the talk by Edward Witten, he said that in the review that Weinberg wrote in 1997, he had the point of view of regarding the standard model as an effective field theory. So I wonder when did people switch to this viewpoint? So when, or maybe if Weinberg was the first to realize this, and when this occurred, or maybe if there was a change of attitude of the community, and when this happened. So maybe either Edward or Howard can answer.
You're muted, Howard. Howard, you're muted.
Now you're unmuted, please.
We still don't hear him, I think. Yes, not muted, but we don't hear him, I think.
Howard, we're not hearing you.
He's not muted, so I don't know why. Howard?
Perhaps unplugging and replugging the headphones might do it.
Is that working?
Yes. Yeah.
Okay, sorry. I was just going to say that I think it was beginning to happen in the 80s after the basic picture of effective field theory was in process, and also because string theory was beginning to, string theory and other ways of thinking of beyond grand unification and beyond were beginning to become current. So I know that certainly by that time, renormalizable quantum field theory was, we understood why it was not necessary to assume renormalizability to get the good consequences from quantum field theory. And the question is, it was just really what happened. I mean, another possibility, which nobody mentioned because it's kind of silly, but is, I think, logically possible is that it's just turtles all the way down. And you have a tower of effective theories, and nature keeps surprising you as you go to shorter and shorter distances. Now, maybe that's impossible with gravity. I'm not certain, but
Edward, do you want to add anything?
Well, it's an interesting question whether that's impossible with gravity. I never really thought about that. Without gravity, certainly logically conceivable, and some have advocated it.
Right.
Especially people who are not particle physicists. Sometimes hear them advocating it. My only other comment is that we shouldn't underestimate the role of grand unification in this, because grand unified theories were the original concrete examples where the standard model, not just hypothetically, but in real life, was a low energy effective field theory of something that was actually seriously put forward. And even today has a lot of attraction.
Thanks a lot. Thanks a lot. So any other question? I see Alberto Nicolis raise his hands. Please, Alberto, are you unmuted? Please.
Hear me?
Yes.
Hi, so I also have a question for Georgi. So, and I'm not sure exactly what Weinberg's viewpoint or contribution was in this, but when we have a weakly coupled theory with heavy particles and light particles, we define the low energy theory by, at least at the cartoon level, by integrating out the heavy particles, meaning really doing the path integral over the heavy particles. However, in cases of strongly coupled theories like EQCD, talk about the chiral Lagrangian for the pions, we don't have this description at hand. We don't have the pions as fundamental fields in the original Lagrangian. So there, as far as I can tell, the most practical approach is a bottom-up approach in which we parameterize the low energy theory in terms of the pions according to the symmetries. And then if we are strong enough, we match the parameters to the UV, to the predictions of the UV theory for certain amplitudes, let's say, at low energies. Now, is there a more direct definition of the low energy effective field theory that mimics the one that we have for weakly coupled theories? Is the question clear?
I'm not sure I understand the question, but let me first of all say that integrating out, even in weakly coupled theories, is not exactly the right thing to do. The right thing to do is to match at the boundary. And that looks like integrating out in simple cases, but in loops, it's simply more complicated than that. Beyond that, I'm not quite sure what you mean by the precise definition of the low energy theory, because it's phenomenologically fuzzy, since we will at low energies be always sensitive to some finite number of parameters and to a given accuracy. But what we can learn is what the symmetries are and what the leading interactions are, and something about the higher dimension operators.
So perhaps to be a little more explicit, so I'm referring, for instance, I've read recently your view, I think from the 90s, about effective. And my understanding about the subtleties of integrating out is that integrating out would be a perfect definition of the effective theory if we didn't perform the derivative expansion. I mean, if we kept the full non-local structure, then it's just an intermediate step to compute the low energy correlation functions, let's say. Sorry, the correlation function for the light field. The complications arise when we do the derivative expansion, because that changes completely the structure of the V divergences.
Correct.
Okay, so now suppose we don't even do the derivative expansion. Okay, so we have the integrating out procedure now is a perfect definition of the effective theory for the light fields, let's say. Now, is there an equivalent definition in the case in which the light degrees of freedom are not even part of the fundamental Lagrangian, like for the pions, for instance?
Not that I know of. I mean, because I wouldn't know how to deal with such a general. I think one way of maybe what you're asking is whether there's a way of thinking directly about non-local theories, and I don't know of one.
Okay, thank you.
Howard, I think maybe Alberto was asking, like, is this your question, Alberto? Like, we could imagine taking the ultraviolet theory, we don't have any pions, but putting some external sources that couple to the chiral currents. And then we can just ask what we get for the sort of we integrate things out, and then we can see that the effective theory that we get for the currents looks like it has sort of light poles in it that are mediated by pions and so on. And then we'd write, and we would try to write an effective, a different effective. We can then integrate light things in order to reproduce all of those correlation functions.
Something like
Is that the sort of thing you were imagining? Okay. Yeah.
Like that, meaning what you're proposing with external currents will be now the generating functional of certain correlation functions, right? And so the Legendre transform of that would be more like the quantum effective action associated with the chiral Lagrangian, would not be directly the chiral Lagrangian, something like that.
Yeah, but then you transform it back and see the chiral Lagrangian in a derivative expansion. I think it sounds like very much the same thing. It doesn't matter that, I mean, it doesn't matter that you don't see the pions there. If you're an experimentalist, you would just couple to some external sources that produce the pions anyway, and you don't know how they're, yeah. So, yeah.
I mean, one thing that Steve said early on in his career that I've never really understood well enough to follow up is this, in a sense, this notion of integrating in. And he showed that one could add fields corresponding to composite particles and reduce make the theory more perturbative. And that's a very attractive idea, but I don't know of anybody that's ever really made it work.
Thanks.
Okay, I see that there are 3 other questions. Maybe we can quickly go with all of them, and then we will conclude. So Alexander Westphal, please.
Yes. You hear me?
Yes, we do. Please.
Okay. Yeah. Thanks, Nima. I mean, it's just there was a discussion in the chat, and I felt maybe I just put it to Nima. We were discussing about your argument about review of Weinberg's argument of the anthropic reasoning for the CC. You had this toy landscape. Of course, that argument depends on the prior of how the small lambda back here close to 0 are distributed. And
yeah.
Of course, it's flat number frequency and number distribution. But can you estimate, like, for instance, say,
well, so let me
Todd's
just
vacuum inflation plus
yeah, maybe I'll make a few correct statements. One of them is that Weinberg, one of the greatest things about him in this context especially is that he managed in all these like stupid 10 years of dumb philosophical polemic debates with essentially no content to avoid it entirely, having contented himself with having made a prediction, right? And having made a correct prediction. Of course, we don't know how to think about the measures, how to think about all of that stuff. That's all related to the business about how the landscape is populated. However, There is an aspect, which that's what I was stressing, is not philosophy, which is simply that if you take that dumb model with like n scalars, it makes it possible without any fine adjustments of the parameters to find a vacuum which looks like ours. It's at least possible. You don't have to fine tune anything. It's at least possible. They exist. Once they exist, and they just exist, I mean, it's just a simple, usual statistical argument. Anyway, literally in that model, there's a little bit more going on because you have to make sure that the central limit theorem in that model would tell you that the distribution gets more and more sharply peaked around the mean. You have to make sure that that actually overlaps zero. So you have to do a tiny bit more work in that model to make sure that it overlaps zero. But if it overlaps zero, you have a flat distribution. And of course, that flat distribution of vacua, how that translates into whether or not it's realized and how it's realized, that's a whole morass that I don't even want to touch. It just makes it possible to find some. And then past that point, I mean, it's just you can say all the mumbo jumbo you want, but Steve said the reasonable thing. He said, look, if this is the explanation for why the cosmological constant is small, it shouldn't be too much smaller than the value that would rip us apart. If it was 100 billion times smaller than that, then it's not the only explanation. There has to be something else explaining it, right? So it's just at that level. But it's not a theory. I like to think about the sort of landscape picture as a cartoon. It doesn't even deserve the dignity of a theory yet. It's kind of a cartoon for what a theory might look like. But let me just make one more point, which is that it's conceivable that the landscape looks in such a way that totally independent of any issues about measures, you can still make interesting predictions where, for example, solving the cosmological constant problem forces you to do some tuning for the hierarchy problem. So let's say, just as a concrete example, there are two different regions in the landscape. In one of them, there's a low energy SUSY, everything is natural, beautiful, perfect. If you're particle physicist, you want to live there. But you count and you count and you count, and there's 10 to the 40 vacua there. Okay. Then there's another region in the landscape where the SUSY is broken at much higher scales. It's not natural from the particle physics perspective, but in that region, there's 10 to the 200 vacua. And let's say those are the only two regions there are. This region where you have low energy SUSY with 10 to the 40 vacua, this other funny region with 10 to the 200 vacua. Then even though as a particle physicist, you might want to live in the place which is natural from the point of view of the Higgs, there just aren't enough vacua there to solve the cosmological constant. So you might be forced to go to this other regime where SUSY is broken at much higher scales, but simply in order to find a vacuum with a small enough cosmological constant, you could be forced to tune the Higgs mass. So, and those are examples where you can make a prediction without any issues about measures, et cetera, et cetera. So we don't know that the landscape has these favorable conditions to be able to do that, but it's not a priori guaranteed that it doesn't.
Mm-hmm. I agree. It's a good point. It's actually a good example for something that decouples from the measure.
Okay, so Kelly Stelle, please.
Yeah, hi. I have a question, I guess, mainly for Ed, regarding Steve Weinberg's revised attitude towards renormalizability. So if I certainly agree with Weinberg and Kim Gomez that you can renormalize a non-renormalizable theory, you just keep on doing it forever and ever and ever. But the question is really, to what extent is renormalizability still a guide at low energies for what you should look at? And a classic example would be gravity itself, for which we don't, the low energy Einstein-Hilbert theory is not renormalizable. So what is one supposed to do with it? Or another example would be a nonlinear sigma model for pions, not yet knowing about an underlying QCD. If you just say that any good theory, maybe there's a hidden word, acceptable or good, that the low energy theory should be renormalizable. Is that what he was thinking? Or can it be articulated more clearly?
Well, one statement is that the low energy theory looks renormalizable regardless of what's happening at short distances. But our ability to even know about gravity is exceptional because it's unrenormalizable. Obviously, only because gravitational forces add, we know that gravity exists. Anything nearly as weak as gravity, if the charge is canceled, we wouldn't know about it.
So suppose I give you a nonlinear sigma model for pion theory. which you, of course, know a lot about, and you didn't yet know how to derive it from an underlying QCD. What would its non-renormalizability tell you to do?
Well, a non-renormalizable theory, according to Weinberg, is good up to a certain energy at which there's a cutoff, at which you need a better theory. So I'm not sure, in your example with the pions, are we supposed to know maybe from experiment that the low energy theory is breaking down below a GeV? Then we would know that at a GeV we need a better theory.
Yes, in the nonlinear sigma model, you've got a dimensional parameter, which is the pion, which is f pi, and f pi sets the scale at which things must go wrong, or 4 pi times f pi, or whatever it is. But there are dimensions in.
Both of the examples have the feature that ignoring the leading irrelevant interactions, the theory is free.
So, well, that's certainly true, and that's a limit.
So in that sense, that the leading thing is renormalizable in the most trivial sense of being free, and so all of the first interesting interactions are coming from the irrelevant couplings. In the case of gravity, as Edward says, we notice it because gravity adds up. For pions, we notice it because pions couple to nucleons, and we scattered them in experiments and so on. So, yeah.
I certainly agree that they're free at the leading order, but that isn't much of a guide then. If every acceptable theory is supposed to be renormalizable at low enough energies.
Well, I don't think that Weinberg wanted effective field theory to be the last word. He was explaining that everything we know can be described by effective field theory, but in that remark I quoted at the very end of the third of his lectures that I talked about, which is the one from just a couple of years ago, he was encouraging the younger generation of physicists to discover what's behind the effective field theory that we observe.
Let me just add that the other special thing about pions is that they're light, and so there is a region where the effective field theory is actually that useful, and in that may not always be the case.
Okay, thanks.
Okay, we have one last question, Matthew Hedrick, please.
Hi, thanks. And I apologize if this was already addressed because I missed the first couple of talks, but I was wondering if any of the speakers had any comments on Weinberg's idea, getting back to this issue of non-renormalizability of gravity and so on, Weinberg's idea of safety for gravity, which is something that, at least in the US, we don't hear too much about, but I think there are groups in Europe that are actively pursuing that. So if there's any comments about that.
The question is about asymptotic safety?
Yeah.
Well, I have a comment about it. That's a question. If there's a fixed point that includes gravity, usually a fixed point is at least a scale invariant theory. But in local quantum field theory, it turns out that fixed points are conformally invariant. That's rather subtle. If there's a fixed point that involves gravity, does one think it's only scale invariant, or does it turn out to be vial invariant? I actually never heard Weinberg express an opinion about that. We had a discussion once where he could have, but he didn't.
Okay, so I think it's time to wrap up. So Stefania, are you around?
Yeah, I'm here.
Okay. So do you want to
I never moved.
say the final words?
Okay, I see that there are a lot of questions still in the chat. So if you want, we have, as always, open our Q&A session on the GGI webpage. So you can use this facility to write your question, and then we will deliver the question to the speaker. Also, in the chat, someone asked me if the slides are available, and I said yes, but I have to ask the speaker to send the slides to us, and then we will publish the slides on the page. As a final thing, I just want to thank Elizabeth, she is with us, and she's attending our session. So it was an honor for us to have her with this special celebration. And of course, I ask all of you for attending this session and make all this celebration very, very exciting, and I think very useful for the young researchers who were here attending the session. So have a good evening for us and day for all the other, and thank you again for being here.
Thank you,
everybody.
Ciao a tutti.
Thank you.
Thank you.
Ciao.
Thank you, everybody.
The GGI Tea Break program go on. So stay tuned with our webpage.
Thank you very much. Thanks for the invitation, guys.
Thanks to
Bye-bye
you.
now.
Thank you.
Bye.
Bye.
Bye.